Are we ready for the second and last spectroscopic technique that we're going to be learning in this course? Right, so we're ready for chapter 15, nuclear magnetic resonance spectroscopy. This is one of the most powerful techniques that we have right now in organic chemistry. Every single organic lab has it. We actually have it at BMCC, a very small one. We don't really use it because it has a really low field, as we will learn in a minute. Uh, but really, industries, pharmaceuticals, textile, proteins, food, biochemistry, everything, any type of research, or even industrial labs, they have an NMR. NMR, of course, the abbreviation comes from nuclear magnetic resonance. That's what we call NMR. And it is right now used as a technique to determine the structure of a particular compound. Even if it's an unknown molecule that we are just creating today, or if it's to identify or to corroborate or to confirm that we are making a known drug, right? For example, if today we make aspirin, right? How do you know that you actually made aspirin? Well, you could say, well, melting point, yes. But remember that melting point is not as deciding, right? Why? Because there are many compounds that share the same melting point of aspirin. So I cannot really say like, oh, this is aspirin because it has this melting point. No, you have to base on other items. Like for example, solubility. Solubility can be another one. Oh, I wanted to do like another benzene ring test. So if my compound has a benzene ring, it should be aspirin. Yeah, it can give you hints, but it's not necessarily like, right, like the most deciding test that you do. So we will do nuclear magnetic resonance. And the applications, well, the application goes from the very STEM, very scientific side, right? In for educational purposes, and it can also go to medicine, medical application. Every time that they take an MRI, they're looking for inflammation or maybe for the presence of a strange kind of body or organelle that is being affected by a wound or by a hit or anything that happens. For example, right here you can see that this person unfortunately has like a tumor in the brain. So tumor, of course, it creates pressure inside of the brain. That pressure is alleviated by the brain by cushioning, right? You will put some cushion to that tumor, so that means water. So the body will protect itself from that strange, right, tumor by putting water around it. And they also cancer cells, they also proliferate or they reproduce by by cellular, right, cell division. That cell division requires a lot of water because it's a lot of hydrolysis that is going on, so the water will be present. Now, why are we talking about water? Why is water so important? Because water contains hydrogen. So even though the first slide didn't really mention clearly, but we are going to be studying or focusing more on hydrogen NMR. There are some other type of NMRs that you can do, but we will focus on hydrogen NMR. We will do a little bit of carbon NMR as well, but basically it's going to be hydrogen NMR. Why hydrogen? Because mostly 99.9% of organic compounds, they all contain hydrogen. Methane, acetone, ethanol, terbutanol, benzene, gasoline, aspirin, ibuprofen, naproxen, amoxicillin, they all contain hydrogen. So that's why it's a very powerful tool, because it contains hydrogen and hydrogen is everywhere. So since hydrogen is in most of the organic compounds, then that's why it is used. Okay, so that big cylinder that you see in the MRI for the ones, for example, I do sports and then I sprain my ankle. So when I sprained my ankle like many years ago, they took an MRI. The MRI, they put my ankle, my entire leg, right, inside of a cylinder, and then it was making some noise. I can really feel the spinning inside of that cylinder. So they told me, please don't move, because if you move, it will ruin the test. And then they finished, and then they got an MRI image, right? So that MRI image is really telling you like what is inside of your body by really this technique, which is called nuclear magnetic resonance. Okay, so in other words, what we are really doing, we call this technique MRI, right? For the ones that have, right, magnetic resonance imaging, MRI is really the same NMR that you do to organic molecules. So now in this case, this person is an organic sample, right? So we're going to be looking at the accumulation of maybe a tumor, or maybe, you know, like maybe the spine has is hurt or has some damage, so they will see the entire body, right? So some people, I mean, they need to be sedated, right? I mean, they have to be sleeping for, to get better results, but it depends from, it varies from patient to patient, right? So let's go to the, what is NMR? NMR is the most powerful technique, right? That right now we have in organic chemistry to determine structure, okay? You will recall from, right, from the previous chapter, right? In the previous chapter, we were saying that IR was really good at determining um, the functional group. So for example, this is propanol, but propanol can also be this way. So we cannot use IR. IR cannot be used to differentiate between those two compounds. So what do we have to use instead? Now we will use 1H NMR. 1H NMR will tell you, it will be able to differentiate by different peaks that you see here, right? Between these two molecules, which one is which. Okay, so it will basically tell you the sequence of the molecules: CH3, CH2, CH2OH, CH3, CH, CH3OH, right? So it will give you by the signals, right, what you have in front of you. Okay, so what is this, the molecule that you are trying to investigate? All right, let's continue. So as I mentioned in the very first slide, so we have many types of NMR. The most commonly used are the hydrogen NMR, carbon NMR. Nitrogen NMR is commonly used for by biochemists and biophysicists, because proteins, amino acids, they contain nitrogen inside. So we want to explore the nitrogen. Now, fluorine for dentists, right? So you want to investigate any corrosion, any enamel protection, or let's say like cements or resins, durability of some resins or new polymers that you're creating. You want to know how well they protect the, right, the I think it's called hydroxyapatite, something like that. It's the mineral that is in your teeth, right? And then phosphorus we find in DNA. Now, uh, why do we need this type of nuclei? Well, remember that elements in the periodic table, I mean, that's the periodic table that has all the elements of the that's existing Earth or in the universe, right? But remember, there's something called isotopes. Isotopes are variants, right? Are like brothers and sisters of the same atom. The only thing is that they don't share the same number of neutrons. So for example, hydrogen 1, right? So that's the most abundant isotope of hydrogen. We have another isotope of hydrogen called deuterium. Deuterium, and then this one is called hydrogen. They're both hydrogen because they have one proton, but this one has only one proton, and this one has a proton and a neutron. Okay, and there is another isotope which is 1,3, okay, deuterium, right? The ones that we will be using mostly are these two, deuterium and hydrogen. The hydrogen NMR, the ones that we study in this technique is 1H NMR, which is this one. Oh, professor, if we put deuterium in your sample, can you see it too? No, you cannot see it. You won't be able to see deuterium because deuterium is 2H. Hydrogen is 1H NMR. Okay, so you will be able to see only 1H NMR and no deuterium. That's actually an advantage because we can make invisible some hydrogens by doing deuterium label. Okay, so we call it label. So for example, if you want right, methanol. In this sample, I want to see the CH3, but I don't want to see the H. Okay, so you don't want to see the OH? That's okay. Let's replace that H with a deuterium. So you will see this one, but you will not see the deuterium. You can do the opposite. You can do CD3OH. You replace one with deuterium and the other one is not deuterated. So in your signal, you will see the peak for the OH. and not the one for the CH3. That process is called labeling. You label a molecule with a particular isotope. You enrich it. You enrich the molecule with a silent or purposely, visible isotope. Right? So in the other cases, we have hydrogen 1, we have carbon 13, nitrogen 15, right? Phosphorus 31, right? So that's one where few of them. There are many, They are not these are not the only ones. These are normally used for in organic chemistry because we have a lot of molecules with these atoms. So in the case of hydrogen, we don't need to enrich anything. Why? Because all the hydrogen, the naturally abundant hydrogen in nature is 1H. So we don't need to enrich anything. Unfortunately for carbon, that's not the case. The most abundant isotope for carbon is carbon 12. Carbon 13 is very small in percent. So if you guys want to study, right, this molecule about carbon NMR, maybe it's too weak signal is the one that you're going to be observing. Why? Because it's too little. Carbon 13 is very small compared to the amount that you have of carbon 12. You have mostly carbon 12, but carbon 12 is not NMR active. You need carbon 13. So what you normally do is you enrich your methanol or your molecule with carbon 13. Okay, so there are different ways how to enrich or how to replace the isotope. Maybe when you synthesize, you use a label with carbon 13. Same thing with nitrogen. The most abundant isotope of nitrogen is nitrogen 14. So nitrogen 15 is not the most abundant. So what should you do? You have to enrich your protein with nitrogen 15. Phosphorus, the same thing. The most abundant isotope of phosphorus is phosphorus 32. Phosphorus 31 is not as abundant. So you have to enrich your DNA, right? Which is the one that has the phosphorus with phosphorus 31. And then you will be able to see it. So in other words, what I'm trying to tell you is that out of those NMR active, right? NMR active isotopes, right? The most convenient and the best is hydrogen 1, right? 1H is the most convenient because it's naturally abundant. You don't need to enrich anything. As you make it, let's say I'm making something, so let's say like this piece of plastic, right? This plastic, right? This one. I want to study this plastic by NMR. I don't need to enrich it. Why? Because it's already made with 1H. So I can just put it directly in the sample, in the machine, and the machine will tell me what is inside, right? Or if it's pure, or, what is it made of, different things that whatever you want to do with 1H NMR. Okay, so in the case of the other ones, yeah, you have to go to a different procedure. The ones that are familiar with biology, you have to do a culture media, to make the nitrogen 15 proteins. You have to feed the bacteria with a specific type of growth, right? The media, right? The media is enriched with some glucose, maybe glucose carbon 13. And then that's how you enrich it with carbon 13. So the bacteria will start eating the glucose that has carbon 13. So when it creates the protein, it will make it with the carbon 13. Same thing with the nitrogen 15. If you want to make a protein with nitrogen 15, well, just give the bacteria, when you're growing the bacteria, give the bacteria nitrogen 15. How? As ammonium chloride or any other salt, sodium nitrate, something. So the bacteria will eat that sodium nitrate or ammonium chloride that has nitrogen 15. So when it makes its own protein, it will have nitrogen 15. Okay? Same thing applies to phosphorus 31. Giving you, this is an experience when I was a student at your age, more or less, guys. I went to a lab and then I had to express bacteria. So I was working with cells, I was working with E. coli, and the E. coli, you had to feed it, right, with some nutrients. Those nutrients were glucose, ammonium chloride, and then when somebody was telling us, oh, I need you to make an NMR sample with carbon 13. Okay, so we knew that we had to feed the bacteria in the nutrients. We have to use labeled, carbon 13 labeled glucose. So when you feed the bacteria will take that glucose and it will incorporate it in the peptide, right? In the protein polymer, biopolymer. Okay, clear? Just giving you some background. Atom with even number, atomic number of mass numbers cannot be observed by NMR. So yeah, that is not a coincidence, right? That this one is 1H, 13, 15, 19, 31. Why are they all odd? Yeah, because they have to be odd number because of the nuclear spin. The nuclear spin is very important. The nuclear spin should be uneven, should be odd. So in that way, it reacts to the magnetic field. So what is that nuclear spin? I never heard about that nuclear spin. Yeah, that's coming in a minute. That's like a scheme of the machine. Yep, the machine, we will not have the opportunity to see the machine from the inside because inside of a box or a cylinder, what we, right, as we saw in the second slide. So we will have a sample, the NMR tube. There's a sample tube, NMR. That NMR will be inside of a magnet. The magnet will create a particular alignment of the spins, of the nuclear spins of the sample. So some of the spins will change the direction, some of the spins will not change the directions. And then once it is magnetized, let's call it like that, the sample is magnetized, then you will use a radio frequency transmitter, right? So you will irradiate your sample with radio frequency, and that radio frequency will take you from the ground state to an excited state. Once that excited state relaxes back down to ground state, it will emit a signal. That signal will be translated by the detector as a peak. Okay, the recorder will give you a peak. So that is very important, this magnetic field, right? Because the magnetic field is the stronger the magnetic field, the stronger the magnet, the better resolution you're gonna get for your results. Okay, smaller molecules, maybe they don't need that much of the magnetic field because there are not that many hydrogens. But if you are trying to study, let's say, cellulose, starch, it's like hundreds of hydrogens. Of course, to differentiate between hydrogen and hydrogen, you need a stronger magnetic field. Magnetic fields can go, I mean, the magnets, the ones I have seen, they can even go to a second floor. So the one that we have in the lab maybe is about 4 feet, like 4 feet or 3 feet tall. That's all. It's very, very small, maybe 1 meter, 1 meter high. 1 meter, right, to your waist, more or less. Imagine to your waist. That's the height of the instrument. That's a 60 megahertz NMR. I heard that they're making now 1600 megahertz. So for that one, you have to go to a second floor. Because remember, this one is the bottom of the machine, that's the top. You have to put the sample from the top of the instrument, the top of the magnet. So you are controlling from the bottom. So to put the magnet, you have to go up the stairs, go and then put the sample from the top. Right? So this is a very, very kind of interesting situation that you have to go to another room, take the stairs or whatever, and then you go to a second floor to put the sample. Of course, they do that for specific samples. You don't use, for example, if I'm trying to study aspirin, I wouldn't use that magnet. It's too much. For aspirin, I would use the one at BMCC, which is only 60 megahertz, right? So that one for 1600 megahertz, yeah, that's for very special cases, right? Oh, it's also something very important. NMR works in solution NMR. There is also something called solid state NMR, but that's mostly to see how let's say compounds behave in the crystal, in their crystal structure. Okay? But to be honest, I mean, what we want for in vitro, right? Cellular activity, binding, everything is in solution, because remember that any type of drugs, any type of binding, enzymes, everything happens inside of your body. And inside of your body is an aqueous environment. It's a solution environment. So if you tell me, like, what is more important, a solution NMR or solid state NMR? Of course, solution NMR is more important and also easier to operate. Okay, great. Okay, so going now to the nuclear spin. What is that nuclear spin, Professor? I never heard about that nuclear, the spin of the nucleus. Yes, so the same way, I'm just gonna close my, okay. So remember that electrons, right? Electron spin, right? That's what we have from GenChem. Electron spin, you have an electron, right? The electron that has the spin up and the spin down, right? So that's the nucleus. The nucleus has a lot of shells, right? And in this case, you have the electrons that they were in pairs. Sometimes they were pairs, sometimes they were unpaired electrons. You could have also unpaired electrons. Okay, those are called the valence electrons. Valence electrons are the outer, right, outermost shell, the ones that is more exposed, and those are called the core electrons. Okay, so those are the ones that are they have a spin, but the electrons they're mostly exposed, right? So those are the ones that are responsible for the chemical bonding. These are the ones that are going to form either ionic bonds or they're going to be forming the covalent bonds. Okay, but the nucleus, right, it also has protons inside, which is normally underestimated. So we normally don't study the protons that much because they don't have like a structure. They are all merged and blend in that sphere, which is what we call a nucleus. But the protons, they happen to have a spin. So that proton, remember these protons are moving constantly as well. Maybe not as much. They don't have that much space as electrons that they can move in the electron cloud, right? The electron cloud, right? There is no nuclear cloud. No, here there is no nuclear cloud, but they are like the imagine like yeah, let's imagine this. This is a proton. The protons are always constantly going to be moving from one side to the other side. So since they have a current, remember every current for the ones that took physics or have taken physics, every current in motion creates a magnetic field. That's what also we call as a nuclear spin. Okay, so the spin, sometimes they're moving in different directions. So you have that all your protons are going to be moving randomly in different directions. Okay, this sphere is really the proton, and then the arrow that you see is the vector for the spin, for the nuclear spin. In this case, it's called nuclear spin. Okay, so that happens in nature. So right now, if I have this piece of plastic, well, this piece of plastic, all the protons, right, all the protons that are inside of this particular carbon and hydrogens, they're moving in random directions. What happens if I put those samples under a magnetic field, a strong magnetic field, right? So here the is rotating, right? The proton is rotating. The rotation creates a magnetic field. So that means that since the proton, which has a positive charge, is moving, then it creates a magnetic field. That magnetic field of the proton reacts to external magnetic field, right? So this one is the scatter magnetic field, the one that I show you here, right? Right here, I was showing you that scatter map of the nuclear spins. But once you apply the external magnetic field, which is B sub zero is the blue arrows, right? So imagine that this sample you put inside of a magnet, and the magnet will change the directions of the directionality of these spins. So some of them will go with the magnetic field, and some of them will go against the magnetic field. Okay, so they will respond differently. So, and then how do you know, professor, for example, here, how do you know that 4 are going to go up and 3 are going to go down? It depends. That distribution of the number of spins against or in favor, it depends on the chemical nature of the proton, okay? So in other words, what I'm trying to, and then that's the beauty of NMR. So for example, right? So in that particular case, you had 4 in favor and 3 against, right? Maybe another case will be 2 in favor, 5 against. Who decides that? It depends on the type of hydrogen. Maybe you have ethanol. Maybe that CH3 has that type of distribution. Maybe this CH2 has that type of distribution. And maybe here there's something else. Yeah, something like that. Maybe this OH has this type of distribution. What decides this? The type of hydrogen. The hydrogen, what we call the chemical environment of the hydrogen, will dictate how many spins are in favor, how many spins are against the external magnetic field. Okay, so that's what dictates, and then that's really what is so important. Why? Because that allows me to differentiate between a CH3, a CH2, and an OH. Okay, and even we'll have some other parameters, but that's really what makes the big difference. I don't want all my hydrogens to be identical, because if all the hydrogens are identical, I won't be able to distinguish them. I need something to distinguish them. So they found out that the nuclear spins are not equally distributed for all the hydrogens in nature. Every type of hydrogen will have a different type of alignment, or right, a scatter. right? So that scattering will change from hydrogen and hydrogen, and that will allow us to use the power of NMR. NMR really, the power resides on that particular property, that not all the hydrogens will have the same spin, right? Spin up and down distribution, okay? Good. So what happens later? Well, once it is magnetized, your sample is magnetized, then you will apply the radio frequency. Remember, radio frequency is electromagnetic radiation. Electromagnetic radiation will push, right, the spin in favor, right? Spin in favor, absorbs the radio frequency, radio waves, and it will be promoted to a excited state, the one that goes against the magnetic field. So that energy that is absorbed, it will be relaxed, right? It will go back down and will emit a light or energy. That energy is going to be taken by a detector, and that detector will collect the data. Okay, so it's really that point. So the most important part of distribution is the magnet. The magnet is really what it allows me to distinguish between hydrogens. This part is not. That part is simple. It's just like ground state to excited state, relaxes, and then emits, right? So that's the conventional spectroscopy. That's the spectroscopic part. This one is not a spectroscopy. There is no spectroscopy here, but we need to do this for us to see that response. Okay, good. So the NMR signals, we're going to be focusing on 4 things, okay? So we're going to be very hands-on with the NMR. We're going to be into the details, into the quantum mechanics. There's a lot of quantum mechanics here. Quantum mechanics is about the behavior of the proton and the electrons in the atom. But we're going mostly to the application. Okay, so 4 things to see in an NMR spectrum. And then in the NMR spectrum, you have it in front of you. This one is an NMR spectrum. And you see 4 things. The number of signals. Why do I have 4 signals? 1, 2, 3, 4. I see 4 signals. If you see 4 signals, that means that you have 4 types of hydrogens. Okay, so how do I know number of types of hydrogen? For example, here in this molecule, ethanol, right? You have it on the screen. So this one, how many type of hydrogens? 1, 2, 3. So that's why you have 3 signals. So say like, oh, professor, I thought it was by the number of hydrogen. No, sometimes the hydrogens are grouped. So one group of hydrogen, for example, a CH3 is 1 signal. I know there are 3 hydrogens inside, but they make a CH3. So that means that they are 1 type of hydrogen. Those 3 hydrogens are equivalent. So they behave as 1 signal. Okay. So here you will have 1, 2, 3, 4 signals. So I have 4 types of hydrogens, okay? The chemical shift. The chemical shift is that ruler that you see at the bottom, right? So the units is called ppm, parts per million, but it's nothing about concentration really. It just tells you like how downfield, this is downfield, or how upfield a signal is. And then this is the time when I'm going to introduce you to the reference table. Okay, that reference table, the one I also show you for IR, right? We used it IR in the previous chapter, chapter 14, IR absorption. Now we're going to be using the back. The back is the NMR chemical shift. That's for hydrogen NMR. Okay, so and then it tells you the chemical shift. For example, this one, a CH3, it will show up around 0.9. Hydrogen next to a chlorine will have a 3 to 4 ppms. A hydrogen next to an OH, to an alcohol, it will be 3.4 to 4. A hydrogen OH aromatic is from 4 to 12. See, there's different types of chemical shift that they will tell you that not all the hydrogens will have the same chemical environment, right? So for example, what makes a difference here? So why is this CH3 different from this CH2? Because this CH2 is right next to the OH. So the chemical environment of this CH2 is totally different from the chemical environment of the CH3. This CH3 is 2 spaces away from the oxygen. And why is oxygen so special? Because oxygen is electronegative. Okay, so another case, you have put a bromine there. Of course, that signal is going to be different from this signal. Why? Because this signal is right next to the bromine. This signal is 2 atoms away from the bromine. This is even worse. This is even worse, right? So that's the worst because it's very far away. 1, 2, 3, 5 bonds, right? 1, 2, 3, 4. Sorry, 4 bonds away. No, the hydrogen is here. The hydrogen would be 1, 2, 3, 4, 5 bonds away from the bromine. This hydrogen would be 1, 2, 3, 4 bonds away. This hydrogen would be 1, 2 bonds away from the bromine. So this hydrogen will feel the bromine stronger, right, than this hydrogen. This hydrogen really has to go really far. So the response to the magnetic field will be different, right, in these 2 cases or even these 3 cases. So normally the bromine or any halogen or any electronegative group, electron withdrawing group, will always push the NMR peak more to the left side. We call it downfield. Professor, is the opposite. Down should be to the right. Yes, I know. But NMR is the opposite. So NMR downfield means to the left, and upfield will be to the right. Downfield means that is exposed to electron closer to electronegative groups, right? This one, no. This one is more electron donating. So if you're closer, for example, you tell me like, where is this peak going to be? Okay, that peak is very close to the bromine, so it will be more downfield. What about this one? Well, this one will be maybe here. What about this one? Maybe this one here. This one will be more or less here, right? Because it's the one that is like the farthest away from the bromine. So there is not much effect from that particular bromine, right? All right, so let's go back to the slides. All right, so what else do we see from what you guys can determine from the image that you see in front of you? You see an integration value. Yeah, maybe it's not obvious for you, but these brackets, red brackets are the brackets tell you like how intense it is, the peak. Okay, so that intensity also tells you represents the number of hydrogens that are inside of that peak. Okay. So the area under the curve will also tell you how many hydrogens. So maybe here I have a CH3, maybe here I have a CH4, a CH2, or a CH, or a CH2. Right? So the integration value will tell you how many are inside of that signal. And last one, maybe the most powerful, maybe the most important, is the fact that you guys will have splitting. You see that that peak, it has 3 spikes. That peak has 1 spike. This peak has 1, 2, 3, 4, 5, 6 spikes. And this one has 3 spikes. Why is this one has 3, 1, 6, and 3? Because the signals split. Okay? And how do they split? They split respect to the adjacent or the neighboring hydrogens. If you have a hydrogen next to you, right, that hydrogen will cause a like a magnetic response. For example, I'm CH3 next to a CH2. At the same time that you are recording my information, right, of this CH3, this one is also being magnetized by the magnetic field. Remember, everybody is being magnetized. But if I look at this one is being magnetized, so it will cause a signal response on this one. Even though I'm looking at these hydrogens, the magnetic behavior of this one, the neighbor, will cause a response on that peak. Okay, that's something that we cannot avoid. So it's really the splitting is a property, and you actually use it on our advantage. Okay. Okay, equivalent and non-equivalent hydrogens. In this case, protons. Yeah, we use the term proton the same as a hydrogen. I would say the best way for you guys to determine the equivalent or non-equivalent would be the plane of symmetry. Yeah, we use a plane of symmetry. So, for example, they are telling me like, are these hydrogens equivalent? This CH3? Yes. Why? Because they are attached to the same carbon. They are CH3. Okay. They are single bonded. CH3, remember, double bond is a problem because double bond is rigid, doesn't move. But in this case, the CH3 has free rotation. So that CH3, imagine my 3 fingers that you see right here, right? So they move in any direction. So those 3 hydrogens will be equivalent. What about these CH3s? Now you have 2. Yes, they are equivalent. Why are they equivalent? Because there is a plane of symmetry right here. Always happens that. Okay? There's a plane of symmetry right in the middle, so it's like a mirror image, right? So is this CH3 is mirrored to this side. What about these CH2s? They are also equivalent. Why? Because there is a plane of symmetry. This CH2 is identical to this CH2. What about this one? Same thing. So there's a plane of symmetry here, that one. Professor, is this CH3 also equivalent to this CH3? Yes, they're also equivalent. Is this CH2 equivalent to this CH2? Yes, they're also equivalent. Okay. Is this CH equivalent to this CH? No, because they are not. The plane of symmetry cuts right here. Okay. What about that H? Is this H equivalent to somebody? No, because the plane of symmetry runs right through it. So there is no way you can have a plane of symmetry with respect to the hydrogen. All right. Okay, so those are called, yeah, I think it's good. So I know sometimes I don't really teach it to in in-person classes. Okay, so those are called, okay, this CH3, okay, CH3s are what we call a homotopic hydrogen or homotopic proton. They are equivalent. That means they will have the same chemical shift, okay? Enantiotopic hydrogens, I will use it with another one. They normally apply to CH2s, but CH2 with no chiral center. Okay, CH2 with no chiral center. Those CH2s, we call them enantiotopic. Why enantiotopic? Because if you replace one, let's say like if I use this, instead of saying H, I replace it with X, they become enantiomers, right? X here is one enantiomer. If I switch them, right? This version and the previous versions are enantiomers. Okay, so that's why we call them enantiotopic. Enantiotopic protons or hydrogens are also equivalent. Or once again, what are homotopic hydrogens? Homotopic hydrogens are hydrogen, for example, CH3s. CH3, we call them homotopic hydrogens because they are CH3, it's a big group, CH3. Okay, so those are the hydrogens. In a homotopic hydrogens, my bad, it's hydrogens. Because anytime that you say homotopic, is this homotopic? Yes, homotopic respect to who? Respect to this one. You cannot say like only one hydrogen is homotopic. No, you have to say like this is homotopic respect to this. So in this question, they're asking me, are these three hydrogens homotopic? Yes, there's three homotopic. Why? Because they're attached to the same carbon. Okay. What about these ones? They are called enantiotopic. Why are they called enantiotopic? Because of the reason I told you before. But really, what makes them enantiotopic is that they are CH2s, okay, and there is no chiral center. That's the practical way to see it, okay? What about this one? The homotopic, any CH3. Any CH3 is homotopic. What about the CH2? CH2s, right? The hydrogens are in the CH2 because it's two of them. So if there is no chiral center, then they are called enantiotopic hydrogens. What if you have a molecule that has a chiral center? Chlorine, hydrogen, bromine. And what about this CH3? CH3s are always homotopic. Therefore, they're all equivalent. That means that all these H's are the same. Okay. Now, what happened with the CH2? Okay, now this is an issue. That CH2 has a problem because these guys were enantiotopic if there was no chiral center. But now this molecule has a chiral center. Since this molecule has a chiral center, now the CH2s, they are not equivalent. They are not equivalent. So these CH2s are called diastereotopic hydrogens or protons, right? And they are non-equivalent. Very important to remember that. That means that these H's are not going to be, they're going to give you different signals. This one will have a peak, and this one will have another peak. What about this one? No, these three will have one single peak for all three. Oh, Professor, I see here another CH2. Is that one also going to be diastereotopic? Yes, they're also going to be diastereotopic. The diastereotopic hydrogens, they are always going to be different, only if they have a chiral center. Right? The chiral center has to be present anywhere in the molecule. Even if the molecule is like 50 carbons away, is that still, if the chiral center is right here, is this CH2 still going to be diastereotopic? Yes. Why? Because the chiral center is somewhere in the molecule. So that chiral center will create these two hydrogens to be different. Because even though you say, like, oh, but the hydrogens, they rotate. How come? Yes, but at the time that you rotate, your chiral center also rotates, right? It will also rotate. So if this rotates, so let's say my indexes, right, are facing. If I rotate this to the other side, then this one is also going to rotate. So they are not always going to be under the same chemical environment. So that's what makes them different. Okay, so homotopic hydrogens and antiotopic hydrogens, diastereotopic hydrogens. So in my problems, I mean the problems, quizzes, and exams, I will avoid these diastereotopic hydrogens, okay? Just to make it a little bit more easier for you guys to do the analysis, I will avoid the stereotopic hydrogens for you guys to do assignments, but I still want you guys to be aware of their existence. I want you to know what is a diastereotopic and why they create two different hydrogens. Once again, why do they create two different hydrogens? Because the chiral center, right, creates a different environment. If one CH2 rotates, well, the chiral center is also going to rotate. Right? So it will rotate, and then these hydrogens are not going to be the same. So for example, one is going to be facing my ring. If you rotate, now the other one, right? So this one will also rotate. They will create different types of species. Okay. Okay, good. So that's the idea for and then here, let's complete that idea with these examples. These are they are chemical equivalent. Why? Because there is a plane of symmetry right here. Plane of symmetry. That CH2 is equivalent to that CH2. Oh, professor, but is there a chiral center? No, no chiral center. CH3, CH2, C double O. There is no chiral center. Therefore, these guys are called enantiotopic, correct? And then this to this, they are equivalent. Here, professor, that CH3, are they equivalent? Yes. Any CH3s, they are always equivalent. Okay. What about the CH2? Yeah, that CH2, the hydrogen of the CH2 are not going to be equivalent, but they are not asking us that, right? They're asking us, what about the the green boxes? So if you ask me like this one, for example, these are equivalent. Why? Because there is no chiral center. No chiral center, no chiral center, no chiral center. So there is a plane of symmetry right here. If you ask me about that CH2, right? This CH2 right here, H and H, yeah, these guys could be diastereotopic. They will be diastereotopic. Yes, that's correct. But they're not asking that, asking us in this particular slide. Here, see, these protons are not chemically equivalent. Why? Because they are diastereotopic. They are a CH2, and then there is a chiral center. That's my chiral center right here, chiral center right there. So that makes it different. Oh, that means that these CH2s are also non-equivalent? Yes, that's correct. They are also non-equivalent. Okay. What about these hydrogens? If there is this hydrogen is equivalent to this hydrogen? No, because this hydrogen faces the OH. This hydrogen faces nobody. So you will not, they will not be equivalent. Okay. So let's see how many hydrogens we have. Yeah, let's go. Let's give some examples. How many signals do you have in this compound? Is there a plane of symmetry? No. So I'm expecting one signal, two signals, three signals. I'm talking about one NMR, right? One NMR. 1, 2, and 3. Why not this one? Because this one has no hydrogens. And the oxygen has no hydrogens, of course. 3 NMR peaks, 3 peaks. Okay. Let's say, oh, let's do carbon. What about carbon? Can carbon also be studied the same way? Yes, you can also study carbon the same way. Let's use red ink for that. For carbon, how many carbons? Okay, 1, 2, 3, 4. In this case, they are all 4 carbons. Here, 3 H's, right? three hydrogen signals. In the carbon one, right? There is no plane of symmetry, therefore they're all different. Carbon. Now we see this carbon because this is a carbon. Four carbons. 1, 2, 3, 4. All right. Okay. How many hydrogen? Hydrogen NMR. Is it a plane of symmetry? Yes, there is a plane of symmetry right here. I can cut the molecule right in the middle. So that means that this H is going to be the same as this H. And this H is going to be the same as this H. Right? This to this, and this to this. Are these two equivalent? No, they are not equivalent. Why? Because this one is closer to an OH, and this one is closer to a Cl. So these are not the same. Okay, so I will say how many hydrogens? 1 and 2. 2 hydrogens. What about carbon? Well, in carbon, yeah, same thing, right? This one is equivalent to this carbon, right? Number of carbons. That's 1, 2, 3, and 4. Why are these not equivalent? Because this one is next to an OH and this one is next to a Cl. So of course they cannot be equivalent. So 4 carbons here. Okay. Let's do another one. Yeah. How many hydrogens and how many carbons? Let's do for carbon. Carbons are easier. So I don't find symmetry here, right? Carbon, 1, 2, 3. Oh, what about this one? Yes, they are equivalent. These are equivalent because it's a split. It's a symmetrical split. Say like, professor, but this one is closer to the oxygen. This one is farther from the oxygen. Yes, but remember single bond, so it will rotate. So then that CH2 will change to same positions. So it will be 1, 2, 3, and 4. 4 carbons. Every symmetrical split will be is definitely their equivalents. Those hydrogens and those carbons will be equivalent. Oh, but professor, but I don't find a plane of symmetry. No, but I mean, there is, but it's just the zigzag. It doesn't really help. So this plane of symmetry is really like right here. You're cutting it right in the middle, right? Okay, next, hydrogens. Let's see hydrogens. Yeah, that's a CH3. There is no chiral centers. Great. Hydrogen, hydrogen, hydrogen. And also these two are identical hydrogen. 1, 2, 3, 4. 4 hydrogens. Okay. Another molecule. Dun, dun, dun. Okay, this one. How many hydrogens and how many carbons? Carbons. Nitrogen is not a carbon. This one is 1 carbon. 1. This is a split, symmetrical split, because it's a CH2 and CH3 is symmetrical. So that means that they're equivalent. 1, 2, 3. 3 carbons. Okay. This one with this one, they're symmetrical, and this one with this one, symmetrical. You can, where is your plane of symmetry? Right here. Right? It's crossing the molecule. 1, 2, 3. What about hydrogens? Okay, for hydrogens, you have also 1 type of hydrogen, 2 types of hydrogen, 3 types of hydrogen, 4 types of hydrogen. What about these guys? Well, this is the reflection of this. This is the reflection of this, so they don't count. 1, 2, 3, 4. 4 carbon, 4 hydrogens. Another one. Yeah, this one. How many hydrogens and how many carbons? Okay, plane of symmetry. Yes, there's a plane of symmetry right here. That means that for carbons, this is the same as this. 1, 2, 3. What about hydrogens? Same. 1, 2, 3. Okay. Double bond. Professor, you were talking about double bonds before. What happened with double bonds? Okay, double bonds are like this. Okay. Number of hydrogens, number of carbons. Carbons, the molecule is not symmetrical, right? I don't see a symmetrical split. I don't see plane of symmetry. So carbons, 1, 2, 3, 4, 5. 5 carbons. Hydrogens. This is a hydrogen group, CH3. This is a CH2, but I don't see a chiral center, so they are the same. 1, 2. This is a hydrogen. This is a hydrogen. So 1, 2, 3, 4, and 5. Okay, 5. These are not the same. So, professor, but if I rotate, it will be the same. No, they are not the same. They are not the same. Double bonds, they lock the, remember, they lock the rotation. They block the, they inhibit the rotation. So therefore, these hydrogens are not going to be identical. They will be have each one peak. 1, 2, 3, 4, 5. 5 hydrogens. Okay. Right, so that's how to determine really the hydrogens, number of carbons for each, for different molecules. Okay, let me see another one, a little bit more complicated, right? Because you always say like, oh, you go very easy, and then on the quiz and the exam is a mess. Yes. Let's see here. Yeah. How many carbon peaks? How many hydrogen peaks? Okay, carbon. Carbon is the easiest. Is there any plane of symmetry? No, I don't see plane of symmetry. The ring doesn't have a plane of symmetry, has a chlorine, has an ethyl, has a carboxyl. There's no way I can find a plane of symmetry. So 1 carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9. There is no plane of, this one is not symmetrical. This is not, these are not equivalent. Why? Because this one is 2 bonds away from the chlorine, and this one is, well, actually, yeah, but this one is next to an ethyl. This one has no ethyl nearby. So that makes a different chemical environment. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, hydrogens. 1, this one has no hydrogen. 2, 3, 4, 5, and 6. 6 hydrogens. Why this one no, professor? Because that one doesn't have a hydrogen. That one already has 4 bonds. 1, 2, 3, 4. This one already has 4 bonds. 1, 2, 3, 4. Okay? So you only do the ones that have hydrogens, of course. So in this case, it would be 6 hydrogens and 9 hydrogens. Let's do one with plane of symmetry. Right? Okay, this one. How many hydrogens and how many carbons? Carbons, there is a plane of symmetry. Good. So that means that this carbon is the same as this carbon. So that would be 1, 2, 3, 4. 4 carbons. Okay, once again, 1, 2, 3, and the bottom 4. Okay, hydrogens 1. This is the same as this. Here 2, 3, right? They are the same, and 4. 1, 2, 3, 4. Yes. Ta-da. Good. Okay, so that's how to determine the number of signals, right? Of how many peaks I'm expecting for each, for every camp, right? Okay, let's continue with the lecture. It might be a little bit longer, but I need you guys to be very ready with NMR. NMR and IR is, I'm aware of, MCAT, DCAT, GRE questions that always you guys will see this type of questions. Okay. Okay. Chemical shift. Yeah. Remember where we went over the NMR signals, number of NMR signals, chemical shift, integration, and splitting. We're developing we're elaborating on each of them. Number of signals, how to determine number of signals. Now we will do how to determine the chemical shift. So now we're gonna be to the reference table. Here's how you see, right? I told you this already. The left side is called downfield and the right side is called upfield. Okay, more electronegative atoms, this is the deshielded region, and this is the shielded region. Okay, electronegative atoms de-shield more and move the signal to the left side. Effect decreases with distance. Yes, that's exactly what I was telling you, right? The farther you are away from an electronegative atom, the weaker is going to be the effect. So it will be more shielded. Okay? Electronegative effects are additive. So that means that if you have a fluorine and a chlorine, yeah, both effects will add, meaning that it will be even more de-shielded, more downfield, right? Because they're additive. Okay, so good. TMS, what is the tetramethyl You guys will always see like a very tiny peak. I'll show you right now. It's a tiny peak that you will see. We're going to be doing these practice problems, right? You see right here, right? This is an NMR sample. You see here 0 ppm, this tiny peak. That's not your sample, that's a standard. We use an internal standard in our NMR samples. That's TMS, very small. Here another one, see? 0 TMS. Here 0 TMS. Here 0 TMS. Okay, another one, 0 TMS. Okay, so that doesn't really represent anything. So what it really means is that you guys have a standard, internal standard. So how do you do that, or how does that work? Well, you prepare your sample, put your compound. Let's say you synthesize aspirin or Tylenol today, and then you put a little bit of that powder in a solvent. That solvent should be NMR inactive, having deuterium inside. And then your sample is the only one that's going to be responding to the magnetic field. And then you add a tiny bit of the internal standard. That internal standard will help you to move the ruler, right, to a 0, right? Because you could say like, oh, this one is 3 ppm. Okay, it's 3 ppm respect to what? Respect to this guy. So who is that guy? Tetramethylsilane, which we call TMS. TMS is the abbreviation for that standard, TMS, right? Tetramethylsilane. Okay, so they're all many hydrogens, very stable. It doesn't react with anything, so that's why they chose it as an integral standard. The chemical shift is measured in parts per million, ppms, or delta. You guys will see that delta, that symbol a lot. Okay, that doesn't mean polar or non-polar, right? Delta plus, delta minus. No, it's not about that. It's just the abbreviation for chemical shift. Here you have different fields, right? 60 megahertz, 100 and 300 megahertz. The difference in the power is really respect of the resolution. So for example, here you see that quartet, right, or that splitting is really well separated, kind of like really, I mean, kind of weird type of splitting. Here is more resolved. This one, the bottom is with a 300 megahertz. This one, 300. And this one is with a 60 megahertz. So it depends, right? The resolution of your machine, you guys will get a different, better splitting. For example, that peak versus that peak. Of course, I will prefer that peak, right? This peak will be preferred because it's more resolved. I see the splitting in a better way. This one, I still see the splitting, but you know, it's kind of like not like that as resolved as the one from the 300. And that's 300. Imagine 400, 600, 700. They do have a way better resolution. Okay. Okay, so here, how to predict the de-shielding. Okay, well, this one we will be working with the reference table, right? The reference table will tell you the relative, right, chemical shift for each group, but you here is really represents what happens with the chlorine. For example, this is propyl chloride. Propyl chloride has the 3 carbons. The one that is right next to the chlorine is 3 ppm, 3.3, is more downfield than the second one, right? The second hydrogen. Second carbon has CH2, is going to be 1.6. And that one, the third one is 0.9. See, every peak will be more downfield as they get closer to the chlorine. In this case, chlorine is your electronegative atom. And the effect, right, depends on the electronegativity. For example, fluorine will push it more to the left. Chlorine, medium high. Bromine, medium low. And iodine, medium, right? Medium, you know, really, really low effect. The standard, right, or the baseline is 1 ppm. And then you can see that effect of each of the halogens, right? How strong it is. Of course, fluorine will be the strongest because fluorine is the most electronegative atom that we have in the periodic table. Okay? Methyl CH3s, they have about 9 ppms. Methylene CH2s, 1-2 ppm. Methine is 1.7 ppms. It really depends on the presence of the hydrogen. Like how many hydrogens are present in the carbon, but they are very close. I mean, even though it looks like 0.9, 1.7, oh, that's a lot. That's almost twice. Yeah, but it's really not. You think that the ppms go from 0 up to 12, okay? Here, there's a how to do calculations. You can calculate simulated data, but we're not going to be doing these calculations. You can calculate it, the approximate changes in the chemical shift by doing a formula, but we are not going to do that, okay? So calculate HNMR. We are not going to be calculating HNMR. We will sketch NMRs. That's what's going to be coming next. But these calculations, I mean, you can skip it. Excuse me. Estimated, calculated, real, aromatic hydrogens that are special, right? Because you might say like, why aromatic, why this type of hydrogens, they have, where's my reference table? This type of hydrogens, why are they so, right? If you look at the reference table, you would say like, yeah, I understand that being next to an oxygen, being next to a nitrogen or a halogen will push your signal more downfield, right? As we said, it will be more to the to the left side. But why is aromatic 6 and 8.5 if the hydrogen is next to a carbon? Aromatic, right? So they are like this type of compounds. So you might ask me, what is the electronegative group here? Why is this one at 6 ppm? Sorry, 7 ppms. I don't see the electronegative group. Based on your table, it should be, lower than 7 ppms. The reason is the electromagnetic field that is caused by the resonance. Remember, benzene rings, they undergo resonance, and that resonance represents electrons running. Running electrons create a current. The current creates a magnetic field. So there is an additional magnetic field that the external magnetic field has to defeat or to align. So that causes that the benzene ring, the peaks for the benzene ring or the aromatic protons, like we call them, they are going to be always between 7 and 8 ppms. They're going to be even more de-shielded or more downfield than the conventional CHs. Okay, CHs are on the 3 or on this side, but if you have aromatic will be always from 7 to 8 ppms. Okay, so aromatic or benzene rings will always have peaks between 7 and 8 ppms. Good. That's the reference table. That's the one that is very similar to the ones that you guys are getting. Okay. That's another way, visual. Here is as a table, or each functional group that has a hydrogen will have its own value. Are we going to do a table for carbon 13? No, we're not doing a table for carbon 13, only hydrogen 1, right? H1 NMR. Integration. What is integration values? Integration values is sometimes it's a ratio that they ask you to calculate. So in other words, what they are trying to tell you is, for example, I'll show you. So let's say, right, I have a CH3OH. Okay. This one, this CH3 will have more or less a ppm of, let's see, CH3, right? CH3OH. That's an H that is next to an oxygen, next to an OH. Where is that? Here. That's a CH next to an OH. That has between 3.4 and 4 ppms. Let's put it in between 3.7. I will put 3.7 ppms and I will put the signal there. What about the OH, alcohol? Alcohol OHs are here, hydroxylic, between 2 and 4. Let's put it in the middle, right? That's the H. 3. Let's put in 3. Now, how high should it be? Okay, so remember that that peak is represented how many? 3 hydrogens. This peak at 3 should represent only 1 hydrogen. So the area should be only 1. Okay, you see the integration value could be this one 3, and this one should be equal to 1. So the NMR peak is also kind of corresponds, right, to the number of hydrogens that are represented. If this one is CH3, that peak should be like a height or an area, right, under the curve, equivalent to 3 hydrogens, or at least 3 times the area that is for this peak, because the ratio is 3 to 1. Okay, let's do another example. Let's say I have NH2, CH2, CH3. Okay, so let's look at the ppms. Okay, in the case of the ppms, amines, let's look for amines here. Amino 1 to 5. So this one would be, let's say, 2.5 ppms. Okay, a CH next to an NH, right, between 1.5 and 2. Okay, let's round it to 2 ppms. It should be really 1.75, right? But it's gonna be just 2 ppm. And this one is a basic CH3, 0.9. Why 0.9? Well, because it's not right next to the nitrogen, so we can say, right? So this NH2 would be this, right? 2.5. This one is gonna be a 2. That's about the same height. And this one is at 0.9. That should be 3, right? 3 to 2 ratio. So it will be maybe a little bit taller. A little bit taller, right? Because this one represents 3H, this one represents 2H, and this one represents 2H. Professor, here you're not considering splitting. Yes, I'm not doing splitting here yet, because we haven't done splitting in the lecture, in theory, right? I'm just using, single peaks, but really they are not like that. They are split. You guys will see splitting, either doublets or quartets. Yeah, here you will see a different response, okay? So here, assuming no splitting, because some of you might tell me like, oh, professor, what is splitting? I don't understand. I know. We haven't touched splitting yet. That's why I'm making the peak. I'm making like the peaks like this. Very simple. Okay. All right. So that's about integration. That's really what it means. In that particular slide that you had in the last one, sometimes they put you the relative areas. So what you guys have to do is divide it. For example, here I have 27. Which one is the smallest? The smallest is 27. So 27 divided by 27. That's the smallest. Yeah. 40 divided by 27. 28 divided by 27. And 42 divided by 27. Okay, so the first one, of course, is going to be 1. 40 divided by 27. 40.2. 40.2 divided by 27. So the next one is 1.48, 1.49, almost 1.5. Next one, 28.4 divided by 27. That's 1.05, almost 1. And then the next one is 42.2 divided by 27. So 1.56. Okay, so you see the ratios will be here 1, 1.5, 1, and 1.5. Of course, you cannot have 1.5 hydrogens. That means that you have to double it. That means that this one is 2, this one is 3, this one is 2, and this one should also be 3. So those should be the integration values. This peak really represents 2 hydrogens. This peak represents 3 hydrogens. That peak represents 2 hydrogens, and that peak represents 3 hydrogens. Okay, so that's what you do if you see areas, these units, see, this height of units. These units. Just divide by the smallest and then do normalize it. Okay? Yeah, that's exactly what we got, right? 2, 3, 2, 3. Ta-da! Oh, are you gonna be required to get calculators like I did here? No. I will always give you the NMR spectra with the integration values. Okay, so you know how many are inside. All right, so what is the ratio between different protons? Yeah, it's basically the same practice. I mean, you can do it on your own. Let's just please, I just leave you a few seconds here so you can see how to determine the number of protons that are represented in each case. Okay, so maybe let's do the first one. So 33, the smallest could be 33.2, right? 33.2. 33.2, that would be a 1. Let me see, 33, sorry, 48 points, right? I'm here doing this. With 4 divided by 33.2. 1.45. It's almost 1.5. Almost 1.5. So that would be 2, same, 2, 3, 2, 3. Yeah, I'm sure it is like that, right? So work on these ones. So for example, this one is 18.7. No, my smallest is 17.1. Divide everything by 17.1. Here, the smallest is, oh, they're 111 because the values are all very close. 18.9, 19.7, 19.9. They're all very close. So it could be here 1, 1, 1, and 1, and 1, and 1, right? Each could be 1, 1 integration value. All right. Splitting. Okay, the time has arrived. Okay, so that we're talking about splitting. Splitting non-equivalent protons on adjacent carbons have magnetic field that may align or oppose the thermal field, right? So the chemical environment on one neighboring hydrogen might affect your signal. So even though I have a signal, an independent signal, but the presence of a neighbor will create an effect on my peak. So you guys might have the n+1 rule, right, for the splitting. So for example, if I am a CH3, right? So let me explain it like that. Okay, I'm a CH3. I will have my signal. My signal will be a peak, of course, right? But because I'm next to a CH2, right? That means that CH3 has two neighbors, and the rule says n+1. So you have two neighbors plus 1, 3. That means that my signal is not going to be one single peak. It's going to be a triplet. This one is going to be a triplet. Why again? This is the signal of the CH3, but the neighbor dictates your splitting. This one doesn't tell you that you are a CH3. No, no, no. This is a triplet and 3 because it's a coincidence. But it really, the splitting tells you the number of neighbors. For example, you tell me triplet, 3 minus 1, 2. That means I have two neighbors. That is. Okay. Now let's do, what is the splitting that I expect for that CH2? Okay, that CH2 will have its peak, right? Has a peak. How is the splitting of that one? This neighbor has no hydrogen. This neighbor has 3 hydrogens. 3 plus 1, 4. Quartet. Okay? The signal for this is 4, quartet, and the signal for this is a triplet. Okay? So that's what you guys will see in the NMR spectrum. You will see a quartet and then a triplet. Professor, how do you know that the quartet comes first and then the triplet comes later? Because this one is more de-shielded, it's more downfield, because it's right next to the chlorine. That's why it will be first. It will be more on the left. This one is farther from the chlorine, so it will be more on the right. I don't know the exact chemical shift. I mean, I can tell you a CH next to a chlorine is about 3.5. Okay, 3.5. Now I know. What about this one? Well, this one is farther away. So somewhere in between, right? So if the regular CH3 is 1 and this one is a 3.5, I will put it right in between, about 2 ppms, let's say. Oh, do I need to be accurate with that? No, in those cases, those chemical shifts that are not tabulated, that are not on the table, of course you have to do an approximation. But this one is on the table. So that one you're expected to do it the closer you can. Doesn't have to be on the dot, right? But you know, the best you can, the best approximation you can make. Okay. What else are we missing? Integration. This one is representing a 2H. That's your integration value. And this one is this one. So it should be 3 H's. Okay, so that means that my triplet should actually be bigger. Something like that. You see? That's a perfect NMR representation of this particular molecule. Quartet for this one and triplet for this one. And then I sketch the NMR spectrum. Okay. Good. I mean, definitely we're gonna be doing more example of that, but I'm just gonna go over what we have on the slides here, the lecture. Okay, so non-equivalent protons or adjacent carbons have an field that align to still. Okay, so it's basically the same rule, the same slide. I mean, the same thing. Here's the n+1 rule. If you have one neighbor, sorry, you have no neighbors, it would be a singlet. One neighboring hydrogen doublet, two neighboring hydrogens triplet, three neighboring hydrogens quartet, quintet, sextet, septet, and a multiplet. Multiplet is like when you see like a lot of jacks, like peaks there. I mean, you cannot really identify. When you cannot identify, you cannot call it septet or nonet or nothing. So you just have to call it multiplet. And also, one of the disadvantages of NMR is that sometimes two triplets overlap. If two triplets overlap, I mean, you cannot distinguish there are two triplets, so you call it a multiplet. Or two doublets, right? Two doublets are overlapped, fully overlapped, so you don't know what it is. So that's also a multiplet, you can call it, if they overlap. So yeah, so that's something very important, that the splitting only happens if you are 3 carbons away. It has to be your immediate neighbor. It cannot be your neighbor that is 3, 4 carbons away. No, it has to be your neighbor, right? The next door neighbor. It's not like 2 doors away. No. It has to be the neighbor. Okay? So for example, let me be a little bit more, give you a better example. Okay, so what would be the splitting for this hydrogen, for this CH2? Splitting for this CH2, I mean, neighbor here, nobody. Neighbor here, 2. 2 plus 1, 3. So this guy's going to be a triplet. Can I also split respect to that CH3? No. Has to be your immediate neighbor. Has to be the neighbor that is right next to you. This neighbor, this one is really the neighbor of that CH2. It's not the neighbor of this CH2. Okay? Now this one. Okay, this one. Neighbor on the left. Neighbor on the left, 3. Neighbor on the right, 2, 5. 5 plus 1, 6. This one is going to be a sextet. And you see how it's kind of symmetrical, right? The splitting. Triplet, medium, tall, medium, tiny, medium, tall, tall, medium, tiny, right? So it's the same. What about the splitting of this? This one has the neighbor is a CH2, 2 plus 1, 3. So this guy is a triplet. Okay, great. It looks good. Okay. I enjoy, I mean, really teaching NMR. I mean, I do like it because it's a very, I see it as a game, really, how to elucidate the structure by reading peaks. Okay. Right. So let's see. That was one example. Oh, what is a singlet, right? A singlet would be, let's say you have a CH3. Oh, okay. This one. The neighbor is an oxygen with no hydrogen, right? And so no singlet because it's 1. It's, sorry, 0 neighbor. 0 plus 1, 1. Okay. What about this one? On the left, oxygen, no neighbor. On the right, 3. 3 plus 1, 4. Quartet. How about this one? On the right, nobody. On the left, 2. 2 plus 1, 3. Triplet. Okay. Remember, the splitting helps you with the neighbors. The peak and the chemical shift, whatever is the chemical shift, X, Y, Z, it tells you about the hydrogen. The splitting tells you about the neighbor. Okay. Of course, the integration tells you about the hydrogen. Okay. Those two tell you about the hydrogen in question, the hydrogen of the peak, the chemical shift, and the integration. They tell you about the owner. The splitting tells you about the neighbors, how many neighbors you have, with the n+1 rule, right? So don't forget the n+1. You forget the n+1, basically you are ruining your entire analysis. Okay, yeah, more coupling. I mean, you guys can read this. That's an analysis of tribromo. Here, for example, this one is a triplet. Why is this HA a triplet? Because it has 2. 2 plus 1, right? 3 triplet. What about the orange? HB. Then HB, the neighbor is this one, the one in green. 1, 1 plus 1, 2, doublet. So you have a triplet and you have a doublet. Okay, interesting, right? Very nice. 1, 2 tribromoethane. Okay, how to calculate, right? How to simulate or sketch. That's what we're gonna do right now. How to sketch an NMR for a particular compound. Okay, so that's coming next. But before that, I just want to show you some really conventional NMR peaks that you will see, not only now, but in many situations, really. Ethyl, for example, ethyl is a CH3, as we know, methyl is always a CH3 and a CH2. So the CH3, let's say here you have somebody, right? So if a CH3 and CH2, this CH2, the splitting, is going to be a quartet, right? Because the CH2 is next to a CH3, CH3 plus 1, quartet. So this one is going to be a quartet. And this one is going to be a, right? This one is next to the CH2, 2 plus 1, 3, triplet. So here, if by any reason in the NMR, you see a quartet, followed by a triplet, most likely that's an evidence that you are in front of an ethyl group. And it's always like this, quartet followed by a triplet. Not triplet followed by a quartet. No, it has to be quartet followed by a triplet. That's an ethyl group. What else? A group which is called isopropyl. This is ethyl, isopropyl. Isopropyl, let's say here have a halogen, right? So you guys will have, what is splitting for this H? No neighbor here, 6 plus 1, 7, septet. You guys will have a septet. 1, septet. 1, 2, 3, 4, 5, 6, 7, septet. 1H, of course. And then this ones, these CH3s, they are next to their equivalent, so they're the same. Next to only one hydrogen. 1 plus 1, 2, doublet. Doublet. A really tall doublet. 6 H's. Why is it so tall? Because it's relative to, proportional to 6 hydrogens, right? 6 versus 1, so that's why it's so tall. 6 and 1. Example for isopropyl, I'll show you right now. Isopropyl, where are you? Of course, when I need isopropyl, now I don't see isopropyls. They will show up, don't worry. Oh, this is an ethyl, for example. This is an ethyl. A quartet followed by a triplet. That's an ethyl. Does that mean that nothing could be in between? No, you can have things in between. It's only that this one is RD2. What about this one? I think this is the same. That's a quartet followed by a triplet. See, quartet. 1, 2, 3, 4. 1, 2, 3. Yeah. You see it closer? You will see the details of the quartet. Yes, a quartet. And that's a triplet. See the 3 lines? 3 lines, that's a triplet. What about this one? Yeah, aromatics are more complicated, are more complex. So don't worry about the aromatics. Yeah, when the time comes, we will be discussing about aromatics with clear examples. Aromatics are really a mess. And the last one, that's conventional or very typical peak that you will see in NMR is known as terbutyl. Terbutyl is, they don't have neighbors because you see this carbon right here has no hydrogens. So this CH3 is a singlet, that's a singlet, singlet, singlet. All 3 are singlets. It's 3, 3, 3, 9 hydrogen. So you see a very tall peak all the way on the right side. I mean, not all the way, not as on the right as the TMS, right, the standard, but it will be all the way on the right side as a tall singlet, 9 hydrogens. This is a clear example like what is not an ethyl group. You see the division, the separation between the peaks, right? I'm doing red dots here, but see the dots? The dots are about, this is called the coupling constant. A coupling constant is what we call the separation between the peaks. For example, this one, coupling, 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 coupling. coupling, right? The splitting, right, has a distance, a separation. Sometimes it's very separated, somebody's very tiny. I mean, there's really no splitting. They do have an information. They tell you something about the geometry. They tell you about the 3D arrangement, which are really, we are not going to go into detail with that. Okay, that's really for organic chemistry 3 for the ones that want to take it in the future. But we do have, the study of the J coupling constant. The coupling is that separation of the splits, right? So in other words, what I'm trying to tell you is that this is not an ethyl group. Why? Because the splitting should be kind of comparable, right? So you have to be able, for example, that's a large splitting versus this one is a small splitting. So this is not an ethyl. The splitting should be similar. Even though they might not be identical, but they cannot be like that different. For example, this one is a big separation, big one, big gap. And this gap is very small. So most likely something happened for that particular, right, splitting that is not really falling under the category, right, that we expected it. Okay, so this is not an ethyl group. Why? Because the splitting does not match what it should be expected. Okay. Okay, so next on the slides, we have the NMR analysis. But before we do NMR analysis, let's do NMR sketching. It would definitely help you a lot for the next, to understand basically how to interpret a spectrum. Okay, so let's say that they ask me, let's draw the NMR spectra for this compound. Okay, this one. Like, so they tell me like draw the NMR or predict, right, the NMR spectra with the approximate integration value. Remember, it's integration, chemical shift, right? And splitting, right? So those three items should be in your outcome, right? In your answer. Okay, so my recommendation is look at each of the hydrogens, and then first is identify how many signals we have, right? So I see no symmetry. This is going to give me a peak. This is going to be another peak, and this is going to be another peak. Now I need to predict the splitting. I would say do first the splitting. So in the case of the splitting, this one is neighboring an oxygen with no hydrogen. And of course, it's going to be a singlet. This guy is next to a CH3, right? It's a CH2 next to a CH3. 3 plus 1, 4. This is going to be a quartet. This one is a CH3 next to a CH2. If it's next to a CH2, that means that 2 plus 1, 3 is going to be a triplet. Okay. The integration values are going to be, this one will be 3 hydrogens. This one will be 2 hydrogens, right? And this will be 3 hydrogens. Now the chemical shift. And then that one is, to me, I mean, it definitely is the easiest part, but sometimes we get a little bit complicated with that. So look, find it. What is that? That is a CH next to an oxygen. CH next to an oxygen. CH next to a fluorine. CH next to chlorine. CH next to an alcohol. That's not the case because I'm not next to an alcohol. I'm next to just like an oxygen. Here, CH next to an ether. 3.4 to 4. I would approximate it and make it 3.7, 3.8, 3.7 ppm. What about this one? This one is also a CH next to an ether. So it would also be the same case, right? So just to make it a little bit, to make it not like too close, I would say that this one, right? The range was what? From 3.3 to 3.4. I will make it separated. Since this one has electron donating group, I will put it more shielded, 3.3 ppm. Okay, again, why am I moving this more to the right? Because this one has an electrodonating group. So electrodonating groups, they push the signals to the right side. So if this one was 3.7, this one will be 3.3. Once again, it's an approximation. You guys say, Professor, how do you know it's 0.4? It's an approximation. Okay, why? Because my range, according to this table, goes from 3.3 to 3.4, sorry, 3.3 to 4. So that's why I'm distributing kind of like within that range. This one now, this one is farther away from the oxygen. So a CH3, conventional CH3 would be about 1 ppm. So that one is fine, 1 ppm. So if I have my spectrum, I will have here my 1 ppm, 3.3, and here 3.7. That's okay. You can play with the ruler. It doesn't have to be, you know, a conventional ruler. So here, the 3.1 ppm, 3Hs triplet. Okay, 3Hs triplet. 3Hs. Next one, 3.3 quartet, 2Hs. A little bit smaller, but it's a quartet. 2Hs, see? Slightly smaller. And this one, the 3.7 is a singlet, 3.7, 3Hs. Has to be taller because it's only one, right? It's only a single, it's a singlet. So definitely the area should be equivalent, right, to the area of this one. Okay, and that's the sketch. That's really why you guys have to sketch it. Another one, let's see. Yeah, why not? Sketch this molecule. Okay, same procedure. This one, this is an NH2. Something I didn't mention before is that you don't do a splitting, no splitting if you have to pass through a nitrogen or an oxygen. The splitting only occurs if you pass through carbons. Okay, so from this hydrogen to this hydrogen there is a nitrogen in between, so there is no splitting with nitrogen. So definitely this one is going to be an automatic singlet because there is no neighbor. The splitting doesn't go through nitrogen. They do a split. They do a split, right? This hydrogen is a split because they are going through carbons. Carbons does allow the split. Okay, that's a singlet with a 2H integration. Chemical shift, nitrogen, amino, 1.5, 2.5. Let's do it in between, 2.5 ppm, right? Once again, it's an approximation. This hydrogen and then these hydrogens. These are identical, right? They are equivalent because it's a symmetrical split. Okay, this one is a 1H. That's integration. How many neighbors? Has 3 and 3, 6. 6 plus 1, septet. Septet. Chemical shift. The chemical shift is a CH next to a nitrogen. Okay, CH next to a nitrogen. 1.5 to 2. Let's do it at 2. Let's put it in a 2 ppm. Because the range is very narrow, right? So you just put in 2 ppm. And these are very conventional. These are CH3s, 1 ppm. Doublet, right? Doublet because they are next to 1H only. This is next to an H, this is next to H, just doublet. Integration, 6 H's. Good. I have 2 ppms, 2.5 ppms, and this one is at, oh, my bad. 1 ppm, 2 ppm, 2.5 ppm. Okay, the one at 1 ppm is a doublet, 6 H's, really tall doublet. Right, it's this one. Then it's 2 ppm, septet 1H, very small. 1, 2, 3, 4, 5, 7. Yeah, very small. Well, 6 H's, I forgot here. 1H, and this one 2.5 will be a singlet. Yeah, singlet 2 H's. Yeah, that's it. That will be the sketch, how to sketch this molecules. One more and last one, I would say like, yeah, that's enough with aromatic groups. Actually, I will do one more after this. Okay, so here, how many peaks? Well, first determine the number of peaks. Okay, 1, 2, there is no symmetry here, here. All aromatics, yeah, all the aromatics can be all encapsulated in one single peak. Okay, Aromatic, 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 aromatic. If they have this type of distribution, okay? This one is another one, and this is another one. Okay, this one is a singlet, right? Because there is no neighbor, and it also goes through hydrogen, so singlet. 1H, and the ppms, this one is a carboxyl group. Carboxyl groups are right here, carboxyl, between 10 to 13.2. So let's do it at 12 ppms. What about these aromatics? Aromatics, they always move, aromatic, between 6 and 8.5. So let's put in 7.5 ppm. And as I mentioned before, aromatics, if they are not symmetrical, then you just do any type of, there is really like a really messy splitting. They're all overlapped, so you won't see it. You can just put it as a multiplet. And 4 H's, that's important though, okay? 4 H's, because 4 H's are represented. This one is a CH2, integration of CH2. It has neighbor, this 3 plus 1, 4. That's a quartet. And the ppms, okay. So that's a CH next to an aromatic ring. CH next to an aromatic ring. 2 to 2.2 to 3. Okay, let's do it 3 ppms. Once again, it's an approximation, guys. You don't have to really do a calculation like that is strict. Here, this is a CH3, right? Next to a CH2, 2 plus 1, 3. It's a triplet. And the ppm would be the conventional 1 ppm. Okay, so this one's going to be really long. Here we'll have 1 ppm. What else? I have 3 ppms. What else? I have 7.5 ppms. And now, what else? I have a 12 ppms. Okay, the 12 ppms will be a singlet, very tiny, 1H. The aromatic is going to be messy, right? Multiplet with 4 hydrogens. That's okay, 4 hydrogens. It's just the area, right? It's not really necessarily the height. 3 ppms, 2 H's, quartet. 2 H's, quartet. And at 1 ppm is 3 H's, triplet. 3 H's, triplet. Okay? That's how to represent aromatic, right? In non-symmetrical. Things that are non-symmetrical. The only exception that we will do, well, let's do it here. So the only exception in which there is some symmetry and the NMR will be special is if you guys have this type of distribution. This is called the para distribution, para isomer, right? So in which you have two substituents and the two substituents are opposed to each other. So here you see there is a plane of symmetry. So this hydrogen is symmetrical to this hydrogen, and this hydrogen is symmetrical to this hydrogen. So, and as you see, they are doublets. Why? Because A is neighbor to B, is one neighbor, 1 plus 1, 2. So this one would be a doublet. And B is neighboring A, 1 plus 1, 2. So this is also going to be a doublet. So it will be 2 doublets in the aromatic region. What else? This is the same as this. This is the same as this. What about this? This is a terbutyl. We mentioned that terbutyls, there are 9 H's, right? Singlet. And then the chemical shift for terbutyls are always going to be 1 ppm. Why? Because they are next to a carbon, a plain carbon always. So it won't make that much difference. The aromatic, we say 7.5, right? ppms. Okay. So 1 ppm, and then I have 7.5. I have 9 hydrogen singlet, really tall. And for 7.5, you have 2 doublets. 2 doublets. Tin, 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 tin. Each has two hydrogens, right? Because you have 2 A's and 2 B's. Now, Professor, how do I know which one is the A, which one is the B? Always, whenever you have an electron withdrawing group, for example, bromine, that hydrogen that is closer is the one that's going to be more downfield. That means that this one is going to be A, and this one's going to be B, because A is closer to bromine. And that's going to be 2 H's, 2 H's. Okay, but two doublets. Okay, so do they have to overlap? No, not necessarily have to overlap, but showing it like that, it should be okay. Okay, so don't separate it too much. Remember that the two doublets should be inside of the range. The range for aromatic is 6 and 8.5. Normally the two doublets are close by. They are not overlapping, like fully overlap, but like this distance, like this is a good distance, relative distance that is appropriate for you to show the para substitution. All right. Okay, great. So let's go back to the slides. That's for NMR determination. Let's gonna start the analysis of the spectrum now. So in the case of the spectrum, right? So the first thing you guys have to do, hopefully you guys can see this good. No, I don't know. You guys can see that in a bigger size. Oh yeah, you can. I didn't know. Right. So let's ignore that bottom one. Right? So we're going to do the first one, the top one. Okay. So anytime that you guys are going to do NMR analysis alone, NMR, is first determine your degrees of saturation, C9, H12, right? Degree of saturation, 2 times 9, 18, 18 plus 2 minus 12 divided by 2. That's 20, 20 minus 12, 8, 8 divided by 2, 4. You have 4DUs. Remember what we said about 4DUs? That most likely you guys have a benzene ring. And I can corroborate that because I have 5 here. I have 5 hydrogens in the aromatic region. So that gives me a hint that I have a benzene ring that has only one substituent, because that's the only way I can have 5, right? 5 hydrogens. So this should be the other ones. So what do I have here? Oh, Eureka, I have here the isopropyl, right? Conventional peaks. See? 1, 2, 3, 4, 5, 6, 7. That's isopropyl. 1 and 6. So isopropyl is that particular sequence. So CH and CH3. Right? This one is accepted. And that you have accepted here. 1, 2, 3, 4, 5, 6, 7. This one is the large, by the way, this one is a large version of that peak, right? And 7, so that's accepted. And that's exactly what we need, right? So because you have C9, I already have 6. So 7, 8, and 9. Okay, so that would be my structure. Benzene ring with 5 aromatic available hydrogens, have one single substituent, and that single substituent is isopropyl. I happen to identify isopropyl right here, isopropyl. Accepted, followed by a doublet, 1, 6. Okay, and we need to assign peaks. Assigning peaks means like put here label A, label B, and label C. How could you do that here? Well, here I can label all these guys A. This one I will label it as B, and this one each will label it as C. Okay, that's how you guys are going to do your NMR analysis. Okay, so the peak assignment, you guys propose your structure and then label A, B, C, and on the NMR spectrum, you always say like, this is the peak for A, this one is the peak for B, this one is the peak for C. Okay, makes sense? Good. Next one. So C6, H12O2. Okay. Degree of saturation, 6 times 2, 12. 12 plus 2 minus 12 divided by 2. Okay, 12 minus 12, 2 divided by 2, 1. 1 degree of saturation. Okay, 1 DU. Okay, what should I do now with this spectrum? So I can see here have another septet. Look, 1, 2, 3, 4, 5, 6, 7. If I find a 6 doublet somewhere, then I'm from isopropyl. And I do. I have a doublet 6. Doublet 6, that means it's an isopropyl. So I have an isopropyl again. So what should I do next? Okay, see the remaining. Okay, in the case of the remaining, I have a quartet 2, and a triplet 3. What is that? If you guys remember. Remember that the right quartet followed by a triplet. That's an ethyl. Yes, it's an ethyl. Right now we're just using 30 conventional peaks. Is that always going to be the case? No, not necessarily. That's why this is the beginning. Just have to apply those conventional peaks. So you guys have an isopropyl somewhere, and you have an ethyl somewhere. How do I know that one is to the right, one is to the left? So it doesn't really matter, right? I mean, that's okay. But how do you know that they are not connected? No, they cannot be connected because they are connected, the splitting changes. Because this one is an isopropyl with a septet because it has only 6 neighboring hydrogens. If you put another carbon with hydrogens here, the splitting changes, which is not the case. Okay, so what else do I have? So so far I have 1, 2, 3, 4, 5 carbons. And my formula says 6. I still need to add one more carbon, right? One more carbon. What else? 2 oxygens. What functional group has 1 carbon and 2 oxygens? Esters. Esters have 1 carbon and 2 oxygens. But now there is a big problem now. How the ester can be written 2 ways. COO or OCOO. In other words, is the COO like here COO or is it OCOO? How do I know that? It depends on the chemical shift. The chemical shift tells me that if a hydrogen is next to an ether, which is the O side, right, the oxygen side, the ppm is between 3.3 and 4. If you are next to a COO, where is the COO? Here. Is between 2 and 2.7. So basically, if you have an ester, right, this guy is going to be about 2 ppms. And the oxygen side is going to be around 4 ppms. That's how you will know which one goes to the COO and which one goes to the O. Let's go back to the spectrum. Here, see, the CH2 is closer to the 2 ppms. The CH is close to the 5 ppms. So definitely, well, this is telling me that if the higher ppm is next to the O, that means that the isopropyl is next to the O. So it should be here O, COO. That should be the structure. Okay, the structure should be for that. Once again, how do I know that? Because the COO, right? The CH next to COO is about 2 ppms. And that's what I see here. The ethyl is closer to a 2 ppm range. So this one is noise. This one should be the COO side, right? This side of the ester. Good. Okay, great. Right. So let's go to the next one. Okay, so here they don't give me integration values. They gave it to me to do the calculation. Okay, so we're lazy already how to do the calculation, but let me see, it's double, right? So 6 is my smallest. That would be a 2, 2, 1, 9. Of course, right? Okay, let's do the analysis here. Okay, so first degree of saturation, C10, H14. Oh, all right. So in here, let's change this. 10 times 2, 20, 20 plus 2 minus 14 divided by 2. 22 divided minus 14, 8. 8 divided by 2, 4. So most likely I should have a benzene ring, right? And I confirm that because I have peaks in the 7 ppm range. That's how you know you have a benzene ring. Okay, so but I have 2 and 2. Remember the 2 doublets? What does that mean that you have two doublets in the aromatic range? That means that your aromatic compound has the para substitution. See, the para substitution, opposite sides. Okay, so what is this guy? Okay, so that bump. Okay, why is it like I see bumps sometimes? If you see bumps, that means that most likely those are exchangeable hydrogens. What are exchangeable hydrogens? Those are hydrogens that are acidic like NHs or Hs, like carboxyl or alcohols or amines. Okay. Can it be an amine? No, it cannot be an amine. Why? Because I don't have nitrogens here. There is no nitrogen, so I cannot have an amine. Can I have a carboxyl group? No, I cannot have a carboxyl. Why? Because first, for the carboxyl, you need two oxygens. You only have one. And second, for the carboxyl hydrogen shows up about 10 to 12 ppms, which is not the case. I don't have anything about 10 to 12 ppms because it's not showing me. So it has to be an alcohol. So I should have an alcohol. What about the other side? The other side is dihydrogen singlet. What is dihydrogen singlet? You guys remember? Terbutyl. Terbutyl. Do they match? Let's see. C10, 6, 7, 8, 9, 10. 10, good. 14 hydrogens, 9, 10, 11, 12, 13, 14. 14 hydrogens, 1 oxygen. Done. Okay. That should be my structure for this particular compound. Okay, makes sense? Good. Next one, C8H10. Oh, 2 times 8, 16 plus 2 minus 10 divided by 2. 18 minus 10, 8, 8 divided by 2, 4. Aromatic, definitely. Benzene ring. I confirm that because I have 5 H's aromatic, right? And the aromatic region, 7 ppms, and it's 5. That means that my benzene ring is mono-substituted, has only one substituent. Now I have to look at these guys. Okay, now I don't see the quartet followed by a triplet. I don't see the isopropyl, which is the septet followed by a doublet, and I don't see the terbutyl, the singlet, 9 H's, right? Now I have to use my knowledge. Okay, so in this case, I have a CH2. Okay, so I will use our practice. That peak right here. This one is a CH2. How do you know it's a CH2? Because I have to, the integration is 2. So it should be a CH2. This one. It's a triplet. What does that mean it's a triplet? Triplet minus 1, 2. That means that CH2 is next to another CH2. Oh, I can't write here. All right, so it's a CH2 next to another CH2. That's the peak at about 4 ppm, right? What about that peak around 3 ppms? Okay, that peak around 3 ppms is also CH2. How do you know it's a CH2? Because of the integration, CH2. It's a triplet. Triplet minus 1, 2. That means that it's next to another CH2. Okay, this is a CH2 and this is a CH2, both. So what is that telling me? That's telling me, like, for example, it's telling me the hydrogens will talk. This CH2 will say, like, I am a CH2. I'm the ring finger. I'm next to the middle finger. And the middle finger will say the same thing. I'm a CH2. I'm next to the ring finger. So they will really be reporting on each neighbor. So I'm your neighbor, you're my neighbor, right? So it's the same response. Okay. And what about this 1H? Well, this 1H is can be anything really. It's a CH. No, it cannot be a CH. Why? Why it cannot be a CH? Because here you have already a benzene ring. In a benzene ring, you already are occupying how many carbons? 6 carbons. Here you have 1 and 1. So 6, 7, 8. you can't use 9, right? Because your formula has C8. You have to make sure that always your formula matches with, right, with your NMR proposal. So I cannot be an CH. So what could it be? Oxygen. What could the oxygen do? It can be an alcohol. Okay, let's see. Alcohols between 2 and 4 ppms. So this one is exactly at 2 ppm. So it could be an alcohol. The one at 2 ppms is an alcohol. And it's a singlet because remember that alcohols, they don't split because they are attached to oxygen. So I could have here a CH2, CH2OH. That would be my compound. OH. Okay. If you ask me label it, okay, A, B, C, D, right? Aromatic A. This one. Which one is B and which one is C? Well, this one is clear, right? The OH should be the D. This one, okay. CH hydroxyl is 3 point, right? CH next to an OH, 3.44, which is exactly what I have here. So this one should be the next to the hydroxyl, B, the 3.4, this one, because it's next to the hydroxyl. It gives you a ppm of, right? CH next to H, 3.424. What about that peak? That one would be like a benzylic. Benzylic is what is benzylic? Right here. CH next to a benzene ring, 2.2 to 3. Yeah, perfect. Right. So this is the benzylic. It's 2.2 to 3. Yes, this is the one. So C. Okay. Aromatics, they're all A, B, C, and D. Good. Great. Let's see the next slide. That one is the nitro. That one doesn't. That's just to show you the results. Right. So here's for you to see. That's a triplet. What will be the triplet? This one, right? That's a triplet. Yeah, it makes sense. It's a triplet because it's next to CH2. 2 plus 1, triplet. This one is a 1. Okay, here's enlarged. 1, 2, 3, 4, 5, 6. Yeah, it's this one, the middle one, right? B. Why? Because it has 3 plus 2, 5. 5 plus 1, sextet. That's why you see a sextet for B. And for A is a triplet. Why? Because it has the CH2 neighbor. 2 plus 1, 3, triplet. Right? Here is missing the integration values, but I mean, you can definitely get the integration values. This is a 3, this is a 2, and this is a 2. Okay? Proton NMR for this one, same thing. Quartet, a quartet followed by a triplet. That's an ethyl group, right? And the OH will be right here. Great. This is how to, right, determine the number of signals, the assignments. This one is what I was telling you about the parasubstitution. We will go over this parasubstitution later. You have the ortho and the meta substitution. Is there any way how to differentiate between ortho and meta disubstitution? Yes, but we are not doing it in this course. Okay, you can use NMR to distinguish between those, but it involves, you know, more complex splitting, which is called meta coupling. But we're not doing meta coupling. So if, oh, what should I do then? Can I just write either ortho or meta? Yeah, doesn't matter. You won't get penalized if you write ortho and when it really is meta, because we don't know how to distinguish them. But you should be able to distinguish the para. This one should be clearly drawn. Okay, so it should be really written as a para substitution because the para substitution is the only one that has the two doublets. You can definitely see the two doublets. For the meta, you don't see it. For the ortho, you don't see it. So ortho and meta, that's okay. If you write ortho and or meta, it works. You will get full credit. But for the para substitution, it has to be para substitution. There is no way you can miss the para substitution. Okay, so this one is the para substitution, meta substitution, and ortho substitution. That's the combination of IR and NMR. I will leave this for you guys. I have many here. The resolution is not the best. That's why I don't really use it for um, I don't use it for class. I tell you here, this is phenaceting. This one is a large version of the phenaceting. But please just use it as a practice. I will have a special, right? I will have a special data set for you. Okay, so let's do that right now. All right. Okay, I will stop the sharing. This one is the first example. We'll have few today. This one, okay, C4H10, C4H, sorry, H8 oxygen. So what does that mean? The first thing that you have to do, you are not giving the IR data. I would have one with IR data, but this one we only have the NMR. So first thing to do, as always, degrees of unsaturation. 2 times 8, sorry, 2 times 4, 8, 8 plus 2 minus 8 divided by 2 is 1 du, right? Okay, so it has either a double bond or a ring. Okay, so I see here a quartet followed by a triplet. So this is a CH2 quartet, right? Quartet minus 1, 3. So it's next to CH3. And this one is a CH3, right? It's a CH3 because it's a 3 integration. And it's a triplet minus 1, 2, next to CH2. So that's how you know it's an ethyl. So far my structure has CH3, CH2. What else do I have? So I have that peak, A, B, C, right? So far I already have A, I have B. So now I need, sorry, I have C, my bad, C. Now I need to assign B. B is a CH3, singlet. Singlet, what does that mean, singlet? That has no neighbor, nobody next to it. So what does that mean, nobody next to it? That means that maybe there is a nitrogen next to it. There is a carbon with no hydrogens next to it. It is a COO. It can be an oxygen, something that has no hydrogens. Okay, so that's all I need. So that means that my structure should be something like this. Yes, something like that. So who is in between? Okay, I don't have any more peaks. I'm done, right? Ethyl, right? The 240 ethyl and the CH3. There's nothing else. This one is TMS. This is the standard. I don't use that one. So what else do I have? I have an oxygen. Okay, but remember you also are missing one carbon. 1, 2, 3. You need 4 carbons. You are only using 3. And you have an oxygen. What could that be? Well, I have 1 du. So what else? COO. Okay, so and that's NMR. Really, you just have to use your intuition. You have to to understand the puzzle that you are in front of. For example, nobody told me that I have a COO. So how can I infer that I have COO? By the formula. I have 1 du, that means I have a 1 double bond somewhere. I have a carbon missing and an oxygen missing. How can I have a carbon and an oxygen and a double bond? Well, COO, of course. And then that's exactly how I'm going to complete the piece. Okay, that's that. Good. That's NMR. I know I make it sound very simple when it's not, when you are in front of it for the first time, but that's really the life of NMR. Okay, C8H11N. So 2 times 8, 16, 16 plus 2 minus 11 plus 1. The plus 1 is because you have 1 nitrogen, okay? Okay, so 16, 17, 18, 19. 19 minus 11, 8. 8 divided by 2, 4. Okay, benzene ring. Most likely have a benzene ring. And I can confirm that because I have peaks in the aromatic region. Remember, aromatic region goes from 6 to 8.5. So this is aromatic. Oh, but I see 4. That means that is disubstituted, right? Because the benzene ring has 6 spaces. I have 4. That means it's 2 spaces. Are they parasubstitution? No, they are not parasubstitution. Why? Because I don't see 2 doublets. I see multiplets. So that means that maybe they are ortho. Can they be meta? Yes, they can be meta, but they can be para. They cannot be para because para has a different type of, right, organization. So whatever you guys decide, if you want to do it meta or para, sorry, meta or ortho, that's okay. I'll propose meta because meta is more separated. Okay, so far I have these guys, A, B, C, and D. Right? That's TMS. What is this guy? This one is can it be a CH2? No, I wouldn't really call it CH2. Do you guys notice that this peak is not as sharp as these peaks or this peak, right? So that means that this one is an exchangeable hydrogen. Whenever you see like a shade that is kind of round, it's not as sharp, it's not as defined, that means it's an exchangeable hydrogen. Who is that exchangeable hydrogen? Is that a possibility for me to have an exchangeable hydrogen? Yes, I have a nitrogen. So you have a nitrogen, that means that you have an amino group. So maybe this could be an NH2. Maybe. I'm going to put it as a question mark because I don't know. But I can make that conclusion because of the shape, the line shape of the peak. What else? Quartet. Let me see. You can see it closer. Quartet. You see it? You see it? Yes, I'm sure you guys see the quartet. And this is the triplet. You see the 3 bars? Triplet. What is a quartet followed by a triplet? 2 and 3. An ethyl group. Yes, correct, guys. Correct, correct. Doublet, right? CH2 next to CH3. Okay, so far we have, I think, all the elements. So I have 2 substituents. I have 1 ethyl, and I have a potential NH2. Okay, ethyl and NH2. Now let's make sure that the formula matches. 6 carbons, 6, 7, 8. 8. 1 nitrogen, 11 hydrogens. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Good. That's it. Oh, professor, you didn't look at the chemical shift. Yeah, sometimes you don't have to look at the chemical shift if you see that all your pieces match, right? For example, I put all the pieces together that I have. I put it, I know that my benzene ring has 2 entries, right? Has 2. And I have 2 groups, 1 ethyl and 1 amino. Of course, it has to be one of them will be the ethyl, the other one will be the amino. I cannot put the ethyl and the amino together. Because if I put the ethyl and the amino together, then I will only have 1 substituent. I can't have 1 substituent. I know that I have 2 substituents, right? So you don't necessarily need, but if you want to go over the chemical shift, yes. Amino, 3 point something. Let's see. From 1 to 5. It works. Amino. The ethyl, this ethyl next to the benzene ring, that's a benzylic. Yes, it's a benzylic. This one I see 2.5. Does that work? Let's see. Benzylic from 2.2 to 3. So it works because it's 2.5. Perfect. Aromatic works. That's my structure. Okay. So just follow those, that strategy. That's going to really take you a long way, guys. So how to, digest the NMR by pieces, what this means, what that peak means, what this one means, And if you find some rationale behind it, oh, okay, so this one is the ethyl, this is the amino, and then I need 2 substituents, okay, it should be 1 to each, and then you are done, okay? Oh, the A, I would put the A, maybe let's do it like this. I'm just saving, making it more organized. The ring, I would put it A, that all the hydrogens are A. The amino is B, right? The ethyl is, this one is C, and this one is D. Okay, so that's how you guys do the assignment and then the assign in the NMR. Great. We're moving. We're becoming experts with NMR. Next one. This next one we have again DUs. 2 times 3, 6. 6 plus, sorry, 6 plus 2 minus 7 minus 1 divided by 2. 0. No DUs. Remember, the minus 1 is the halogens are also subtracting, right? Okay, so I don't have quartet followed by a triplet. I don't have septet followed by a doublet. and I don't have the 9, right? The 9 singlet for terbutyl. So I have to do the analysis one by one. What is this guy? This is a CH2. Well, A, B, C, right? Those are the peaks I need to assign. CH2, triplet, CH2. CH2 is because the integration is CH2. Triplet, triplet minus 1, 2. That means there is a CH2 next to a CH2. This guy is also a CH2, but this is a 1, 2, 3, 4, 5, 6 sextet. Sextet minus 1, 5. How can I have 5 neighbors? How can a CH2 have 5 neighbors? You cannot be CH2 next to a CH5. CH5 doesn't exist. But what about if I have CH3 on one side and CH2 on the other side? Does that work? Yes, that works. Right? That's how you can have 5 neighbors. Oh, professor, can I have CH2, CH2, and CH? Yes, you can also have that. But how likely that is? Very unlikely. It's more likely to have CH3 and CH2. Okay, so that means that this guy is going to be a CH2 next to a CH3 and a CH2. And what about this guy? This guy is a CH3. It's a triplet. Triplet minus 1, 2 is the CH3 next to CH2. Okay, I found it. I have all the pieces together. What do you mean the pieces together? It's like this guy is telling me I'm between CH2 and CH3. This is telling me I'm a CH3 next to a CH2. So this part is inside here. Look. And this CH2 is right here. Right? All the pieces connect, right? I'm a CH2 next to CH2. That's this. I'm a CH2 next to CH2. That's this. That's it. And it needs 3 carbons, 3 carbons. So my compound is going to be CH3, CH2, CH2. Am I missing something, which is Cl? Good. Does the numbers match? 2, 4, 7 hydrogens. Yes, 3 carbons, 1 Cl. And the splitting makes sense, right? We just went over the splitting. Now the labeling. Do I need to check this one? Yes, but I know that halogens will always do more downfield, right? So that means that this one should be the A, this one should be the B, and this one should be the C, right? The C is unaffected. Okay, makes sense? Okay, please let me know. We're doing as many problems as we can, right? C7H14O2. DUs, 2 times 7, 14. 14 plus 2 minus 14 divided by 2. 1 DU. Okay, so definitely I have no benzene ring, right? And then I can corroborate that because I don't have 7 ppms. I have COO. Okay, so I have to be careful with the COO. COO can be oxygen, but can be many ways. But I should be suspicious with esters. Esters are always with O2s. Okay. All right. So this one is a CH2 because it's a quartet. Oh, quartet followed by a triplet. Good. It's an ethyl, right? Remember, guys, quartet followed by a triplet, and they have about the same separation. You see the splitting? It's about the same distance. So that's an ethyl. Somewhere I have an ethyl. What else do I have? Oh, 9 hydrogens. Who is 9 hydrogens? Tall singlet 9 hydrogens. Terbutyl. Yes, terbutyl. Terbutyl. That terbutyl, of course, has a neighbor, and then that ethyl is by itself. So far I have how many? 1, 2, 3, 4, 5, 6. I'm missing 1 carbon, right? 1, 2, 3, 4, 5, 6, and then I have 7 carbons. I'm missing 1 carbon, and I need 2 oxygens. So definitely it's exactly what we were thinking, the ester, right? Because I also need 2 oxygens, ester. But there are 2 ways how to write the ester. Or like this, or like this. It depends on what? It depends on the chemical shift, right? Remember, if something is next to a carbon, COO is 2 ppms. If it's next to oxygen, it's 4 ppms. In this case, the ethyl, This one is what is the range for it? This is about 2 ppms. So that means that the ethyl, most likely the ethyl is going to be next to the COO side because it's about 2 ppms. Okay. Professor, is it wrong if I do it the other way? It's not fully wrong, but also it's not correct. That means that you didn't check, you didn't do this analysis that I just did. That COO, the COO side is 2 ppms and the O side is 4 ppms. That analysis is very important because it will allow you to distinguish between, right, which side it is. Okay, so A, B, C, this is B, 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 this one is A, and this one is B. Done. Okay. That is the power of the NMR, 300 NMR. CdCl3, that's the solvent. You see, it's deuterated, has deuterium inside. Okay, so that's what I have for NMR. Now let's do some of the combination, the combo. Let's do some of the combo of what do you call combo? Combo is the IR NMR system. You guys most likely for the exam and the quiz, you guys will receive this combo, meaning that IR peaks and the NMR, the two. Oh, but professor, we just did analysis with NMR. We didn't need IR at all. Yes, it is true. Yeah, you don't have to, but the idea is really to use both tools, right? Both techniques to elucidate the structure of a particular compound. Okay? So for this one, let's just do a couple. I mean, I have many, but let's do just few, right? Okay, so C7 first. C7, let's look at first the IR and then is the NMR. Okay, so C7H14O. So you guys, I'll give you 10 seconds to determine the use. Yes, the U is equal to 1. Okay, so what else should I do? Okay, so I don't have my ruler. Somebody took my ruler. Okay, 3,000 line, right? IR. Yeah, CHSP3. That's it. Nothing here. Okay, so 1720, more or less. 1720, that's a C double O. Below 1400, that is fingerprint. I don't need it. Yeah, that's it. That's really it. All I have. That's all I see. The C double O and the CHSP3. That's all. Okay, so at least I know that DU, right? My single DU is a C double O. Yeah, that's good news. Okay, here. Singlet, singlet, singlet. But the good news is that I have an NiH singlet. That's a terbutyl. Terbutyl. What is this guy? What are these guys? Okay, so 2 H's and 3 H's. What could that be? Okay, that's a CH2 singlet. And that's a CH3 singlet. So how can I have that? Singlet, meaning that doesn't split. So I have that terbutyl. I also have a CH2 singlet. I need to put a COO somewhere. I know that it's a COO because of the IR. The IR is telling me COO. What else? I have a CH3 somewhere. And I have terbutyl. So I need to scramble these groups to put a molecule together without altering the splitting singlet. That means that I can't put the CH2 and the CH3 together. Because if I put the CH2 and CH3 together, they become neighbors. If they become neighbors, they wouldn't be singlets, right? Have to space them. What can I use as a spacer? Oh, professor, why don't you put the COO as a spacer? That works. If you put the COO as a spacer, that works because then they will keep the singlet property, right? Oh, but if you put the CH2 will be neighbor to the terbutyl. That's okay. Why? Because the terbutyl has a carbon that has no hydrogen. So this guy will still be singlet, right? Because if I put it here, this carbon has no neighbors, so it won't split. Okay, let's do it. Corroborate. Singlet, yes. Singlet, yes. Singlets, yes, they're all singlets. C00, this one is a singlet, yeah, count it. C7, H14O, okay. 1, 2, 3, 4, 5, 6, 7, yes. 9, 11, 14, yeah. Oh, I have my C00, good. I have my degree of saturation, yes, because it's my C00. So that structure should be correct. Okay, so that's your outcome for this particular problem. Next. Yeah, this one might look familiar, right? This one. Okay, so DU first. 18, 20, 20 minus 12, 8 for DUs. Okay, for DUs, immediately my conclusion is a benzene ring. Okay, 3000 line. Have an OH. Clearly, this one is an OH. What else could that be here? Can be NHs, right? But I don't have nitrogen, so it is not an NH. Okay, so I have CHSP2. I have CHSP3. I don't have COOs, but I do have the aromatic. Remember the aromatic peaks? CHC aromatic. Those two. Okay, great. Now let's go to the, see, at least I know that I have an OH and it's a benzene ring, right? I confirm it with my DUs. Let's go. Two doublets, Eureka, I'm so lucky. I love when I see two doublets in the aromatic region, because if I see two doublets in the aromatic region, that means that you guys have a benzene ring. Para substitution. Okay. A, B, C, D, E, F. Out of those peaks, which one is the one that looks more like an OH? We know that OHs are not as sharp. They are not as, defined. This one, right? That's the OH, right? It should be the OH. Okay, so you guys have the OH. That means that I have it, right? So I also have the in the IR OH. Okay, let's not put it yet. Okay, so here you guys see it. This one is a quartet followed by a triplet. Quartet followed by a triplet. That means that these are an ethyl. These are ethyls. One ethyl. Right? Ethyl. Those two. But with no neighbors. They cannot have a neighbor, because if you have a neighbor next to the CH2, then you ruin the splitting. So that's a pure a particular ethyl. So it should be one of those. What about this one? This one is a CH2 singlet, meaning that it has no neighbors. Can I put it in the ring? No, if you put it in the ring, you mess the aromatic hydrogens. So it has to be here. What else am I missing? Because this one is a CH2, needs something. The OH, right? 2 and 2. Which one do you put as A? Yeah, I would put the one that is closer to the oxygen. A, B, C. This one is D, E, and F. Do I need to corroborate chemical shift? I mean, you could, but I mean, it's not necessarily. I mean, that CH2 is a 4 because that's a CH what are you here? Alcohols between 3.4 and 4, right? CH next to an OH, C 3.4 and 4. Yeah. And it got pushed because it's not only that, it's also next to a benzene ring. So that's why it gets even more downfield. That's the benzylic region from 2.2 to 3, right? Benzylic, where are you, benzylic? Yeah, 2.2 to 3. That's why the CH2 is about 2.6, right? 2.6 ppms. Great, that's the structure with the assignments. Okay, good. Next one, we have a few more. I will do just a couple more. Many examples. Okay, hopefully you like this one. C7, that's 1 ppm. Sorry, 1 du. 1 du. Right. 1 du, IR 3000. Okay, CHSP3. That's a COO. The COO a little bit higher, 1740. So that means that it could be an ester, right? Remember that there were different types of COOs. The ones that were more on the left side were ester. The one in the middle are ketones, aldehydes, and the one on the right are the amides, right? This one, because it's slightly higher, could clearly be an ester COO. But let's see. Okay, win-win. This is a win-win. Look at this. One, this tiny is one. 1, 2, 3, 4, 5, 6, 7. Septet, 1H, followed by a 6H doublet. That's an isopropyl. It's clearly an isopropyl. Isopropyl, somewhere there is an isopropyl. Now I need these guys. Okay, so what is that? This one is a CH2, right? CH2. Triplet, sorry, triplet -1, 2. So that means a CH2 next to a CH2. Good. What about this one? This C, the letter C. It's also CH2. What is a what? It's a 1, 2, 3, 4, 5, 6. 6 -1, 5. How can I have 5 neighbors? CH3 and CH2, right? The same as before. And what else? The last one. The last one is the hydrogen E is a CH3 triplet -1, 2. Right? So this CH2 is right here. This CH2 is right here. So I have a propyl group, right? Propyl group. So I have isopropyl, and on the other side, as you have a propyl group. And now I need to place the ester. I know this is the ester because the IR told me the ester, also because I have 2 oxygens, and then I'm still missing 1 carbon, right? 7. So I have 1, 2, 3, 4, 5, 6. I'm missing 1 carbon and 2 oxygens. That's ester. So now, but again, you can have ester like this, or you can have ester like this. If it's next to the oxygen, that would be about 4 ppms. If it's next to the carbon, about 2 ppms. Who is high? The isopropyl. See? The isopropyl is about 4.9 ppms, 5 ppms. That should be the one next to the oxygen. What about the propyl? The propyl is about 2 ppms. So that's the next to the COO. And that's my structure. Okay? That 1H is A, this one is B, C, D, D, and this will be E. Each gets assigned. Okay, let's see, one more, I guess. I mean, we have many more, but let's just keep doing this one. Maybe I'll just give you as many examples. You can pause. If you think that you had enough, please, you can just end this lecture. But if you want to see more examples, I have 3 or 4 more examples. I'll just leave it up to you. Okay. But all what I'm going to tell you right now is that I'm just going to keep doing more of these examples. If you want to end it, feel free to do it. But if you want more examples to see more cases, please stay. So I'm going to do as many as I can. All right. All right. So C4H11N. So 8 plus 2 is 0 to use. Okay. You guys will do the formula. You will calculate it, determine it. Okay. That peak looks like a carbon NH. NH. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. 8 + 2 = 0. No NH2 is NH because it has only one hump, right? It's only one bump. So this one is CHSP3, and that's it because the rest is just fingerprint region. Oh, I see something here, but I don't know, around 2600, but I don't know what that could be. Anyway, so far I have only nitrogen, NH, no NH2, I have NH, and CHSP3. Okay. Okay, lucky again. Let me see if I can get it bigger. Yeah. Septet, right? 1, 2, 3, 4, 5, 6, 7. Septet. Followed by a doublet 6 hydrogen. That's an isopropyl. What else do you have? I have a CH3 singlet. And I have one here. That should be the NH. How do you know it's an NH? Because it's kind of distorted. You see, guys, how it's kind of round, it loses the shape. Yeah, that's an exchangeable hydrogen. We were saying that exchangeable hydrogens are carboxyl, OHs, and NHs. Okay, so I need to put the CH3, but I cannot put the CH3 here because if I put it here, I will ruin the splitting. So what am I missing? The NH and then the CH3. A, B, C, D, A, B, C, D. Okay, so how can I corroborate that that is the authentic chemical shift? Because the CH is next to nitrogen. CH is next to nitrogen are between 1.5 and 2 ppms. Yeah, this one is about slightly higher actually. You see, those NMR peaks, reference tables are not as accurate. So for example, this one is about 2.6 and this one is about 2.4. And the table tells me another range, right? That is narrower, right? This one is 1.5 to 2. Yeah, it varies. Once again, so don't really rely that heavily on the reference tables. Okay, so at least it helped me that I have an NH. See, without that information from the IR, I would imagine that it would be an NH2 because automatically you always think it's an NH2. But no, here it's telling you it's an NH. So that's really the role of the IR is to confirm and to corroborate what type of function group you have in front of you. Okay. Next one, once again, if you think that you had enough NMR and IR, please you can just leave. Thank you for watching us and then listening to this lecture. Next, C20, 22, 22 minus 12 divided by 2, that's 10, 5 DUs. Okay, so 5 DUs. What do I have? 3000 line. I have I see something here. I see the two bumps for the aldehydes, 27 and 2800. And of course, the CHSP3, right? That's the COO. That's it. Potentially have an aldehyde. I can see. All right. What do we have here? Yes, I have an aldehyde. How do I know you have an aldehyde? Because you have a peak at now around 9 ppms. If you go to the table, aldehyde, look for aldehyde, aldehyde. I'm sure you found it. Yeah, here. Aldehyde. CH aldehyde between 9 and 10. So that's the aldehyde. Singlet. Has to be singlet. No, not necessarily. Is it? No, doesn't have to be singlet always. Right. Two doublets automatic. Good. Because I know that it's automatic because I have 5DUs. 5DUs are automatic. Oh, I have some CH here. I guess this should be the CHSP2. And these are the automatic peaks, right? The CCC automatic. Anyway, so I have the two doublets. Two doublets, that means there is a para substitution. Okay. What else? What do I have here? I have a CH2 triplet. You see triplet, guys? Triplet minus 1, 2, CH2 divided by, followed by a CH2. This one is a CH2 between what? How many? Where's the splitting? You guys see it. 6, right? Yeah, I think we did this before. 6 minus 1, 5, 5. How many neighbors? A CH3 and a CH2, right? So CH3 and a CH2. It's a propyl. And the last one is a CH3 with a CH2. So this CH2 is here, and this CH3, CH2 is here. So it's a propyl. So I have a propyl somewhere. So I have an aldehyde, I have a propyl. What else? I have an aldehyde somewhere, and that's it, right? Because this one is here, these two are here in the ring, and those 3 peaks are the propyl. That's it. So I don't need to find anything else. Oh, I have 2 oxygens. Two oxygens. And so far, I'm only using 1. I need another oxygen. Where should it go? Can I put the oxygen here? No. Why? Because if I do that, it wouldn't be an aldehyde anymore, right? Goodbye aldehyde if I put the oxygen there. So where should I put it? Yes, put it on the other one. This one should be the oxygen. Okay, that's the one that should have or hold the oxygen. So in one we'll have the aldehyde, and the other one would be CH2, CH2. Okay, aldehyde would be A. This one. Between the two, the most electronegative, the most electron withdrawing is the aldehyde. So this one will be B, this will be C. Oxygen, this one will be the D, E, and F. Yeah. Professor Navarro, why are you putting C and B? I would imagine that oxygen is more electronegative than carbon. So technically B should be more shielded, more upfield. No, COO is more electronegative because of resonance. This one pushes electrons away from the ring. So it pulls electrons, and this one forces the electrons out of the ring. Okay, so that's why COO is more electron withdrawing than oxygen. Oxygen actually does resonance, but towards the ring. The COO conjugated takes it out, right, from the ring. Okay, good. Next one. We have a few more. I should have 2 more. Yeah, let's just do it all. So you guys have no excuses, I mean, to not have enough practice, practice sheets or practice problems for NMR. Okay, so DUs here. Let me think. 10 minus 8, 1 DU. Okay. Oh, I see something very interesting. You guys remember this distorted peak that goes from 3200 to 1800 to 2500? That's a carboxylic acid. Yes, carboxyl, OH, and that's the COO. That's all, right? You should see both of them. So far I know that I have a carboxylic group. And how can I corroborate that? Because if I have a carboxyl group, I should see a peak between 10 and 13.2. And that's exactly what you have. Carboxyl. 11 point something, right? Now these guys, okay, these are easier. CH2. Okay, triplet, right? You guys see it? Let's make it closer. Yeah. Triplet, right? Triplet minus 1, 2. That's a CH2 next to CH2. Good. This one is also CH2. That's also a triplet, so next to CH2. This one is a CH2. This one is a pentet. Okay, pentet. Pentet minus 1, 4. So I have 4 neighboring hydrogens, 2 CH2s, right? 2 CH2s. What does that mean? That means that CH2 is right here. And this CH2 is right here. So I have those two. Okay, so what should it be then? So I have the carboxyl group. Let's use group here. I have the carboxyl group. And I have the CH2s. 3 CH2s, right? And what else? The chlorine. The chlorine as a cap. Count the atoms. 1, 2, 3, 4 carbons. Yes, 4 carbons. 7 hydrogens. 6, 7 hydrogens. 1 chlorine and 2 oxygens. Yeah. 1 DU, right? 1 DU, 1 DU. That's all. They all match in the splitting. Yeah, that should be a triplet. Yes, triplet. That should be a pentet, and that should be a triplet. Perfect. And the last one, and I leave you alone after this. DUs, 10, 12, 12, okay, 1 DU. 3000 line. Okay, this one is an OH, clearly an OH. It could be an NH, but I don't have nitrogens, so OH. CHSP3, COO. Oh, interesting. Okay, remember in my previous case, let me see if I found it, yeah. I know that it's going to use carboxylic acid because the COO and the OH, but the OH was distorted. The OH was distorted. That's how I know this is a carboxylic, COO and distorted OH. This one, I have a COO and I have an OH. How come? And this is not distorted. That means that it's not carboxylic. That means that the COO is somewhere, and somewhere else is the OH. Okay? They are not forming a carboxylic acid. They are two separate functional groups. Okay? Good. Knowing that, let's do that. This one. Wow. Not that easy. Okay. In that case, I have a CH1, 3, and 6. No aromatic, right? Okay, well, at least I know that my OH has to be here. Who has to be the OH? Of course, this one. Professor, how do you know that that's the OH? Because OHs are always one hydrogen only. You don't have OH6. You don't have OH3. You only have OH1. So that one has to be your OH. Okay? CH3 singlet. That's okay. And 6. What could be 6? Okay, so of course it's not a CH6. It's not CH6. So what could that be? Okay, that one should be 2 CH3s symmetrical. Two CH6, right? That are singlet and that they are symmetrical, meaning that they are twins, right? They're attached to the same group. Okay, so what would that be? Okay, so now since I'm right now in the limbo, right? So now is the time to use the chemical shift. So chemical shift, what peak CH3? Well, I know I have a ketone. And I don't have an ester. How do you know that you don't have an ester? Because you have a COO, but you have an oxygen. I cannot have an ester because if I do an ester, it will be 3 oxygens. I don't because I only have 2. So it has to be a ketone or aldehyde. I know it's not an aldehyde because aldehydes give me a chemical shift around 9, 10 ppms. So it has to be a ketone. So that CH3, right, is around 2 ppms. What peak is around 2 ppms? No, 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 no. Okay, no, no triple bond. I don't have enough DUs. No. Benzylic could no, because I don't have enough unsaturations. Allylic, no, I don't have CCC. I already have my COO. No, no. Bromide, no. Iodide, no. Alcohol, no. 2 ppms. Ester, no, I don't have an ester. Acids, I don't have an acid. Carbonyl compound, 2 to 2.7. Yeah, that works. That works, right? The CH next to a COO is to 2.7, which is that one. What else could that be? Aldehyde, I know it's not. OHs, I already know. It cannot be OH3, so it cannot be that one. Phenolic, no. 4 to 12 is 2, no, too low. No, no. Here, amine, no, I don't have nitrogen. Amino, no, I don't have nitrogen. No, I don't have nitrogen. So the only one that really falls for under that category, under my conditions, my formula, my unsaturation, is carbonyl. So that means that CH3 is next to a COO. Okay? And then this one is done. A, B, C. Now, can I put the OH here? No. If I put the OH here, then there is no room for the CH3s. So I have to put another carbon. And this carbon will contain my CH3s. They're singlet, right? Singlet, singlet. And what else am I missing? The OH. This one is a more advanced problem, really. Why? Because I'm making a lot of assumptions, right? So first is that these CH3s, right? They need to be together. I mean, they need to be together because they are twins. They are geminal. So that's why they are a singlet. But they're also singlet because they are next to a carbon that has no hydrogen. I cannot put a hydrogen here. So the OH is a perfect fit because the OH will make it with no hydrogens. And that CH3 has to go next to the COO. Why? Because of the ppms. The chemical shift tells me like this CH3 is next to a COO. I know that because it's of the ppms. The ppms tell me it's a CH3 next to COO. This one is a conventional, very conventional CH3 range, right? Around 1 ppm. And the alcohol, this really helped me from that, right? This one told me like I have an OH. So out of those, the only OH should be that. That got this peak out of the way. So I only got reduced to 2 peaks to analyze. Okay, so that would be the final answer for this compound. That would be the most advanced that we will do, kind of like a more elaborated, a lot of assumptions that you guys have to make for this type of analysis, but that would be it. Okay, so let me know if you guys have any more questions. Remember that you guys can use the NMR and IR table during your quizzes and exams. Take good care of that. Okay, so you guys is posted on the platform, the learning platform, so you can download it as many times as you guys want. All right, so let me know you have questions, and then I'll see you for the next chapter. All right, bye bye.